class imbalance graphs. So when you're ready, the floor is yours. Okay, thank you.
Hello everyone. Today I will present our paper titled Less is More, using buffer node to reduce excessive majority node influence in class imbalanced graphs. This work was conducted by our team at the National University of Singapore.
Sorry. Can you take the microphone closer and can you speak a little bit louder, please?
A bit closer?
Yeah, and louder a little bit, please.
Okay, thank you. We propose a new framework called the buffer graph to tackle a critical issue in graph neural networks. Let's start with the problem. While graph neural networks are great at node classification, standard model assumes the worth is balanced. But as we know, real-world data, like the financial network or citation graphs, is almost never balanced. For example, in this example, for example, in the Ethereum networks, the fraudulent accounts are a tiny minority compared to normal users. The core issue isn't just the number of the nodes. It is the connections. We call it as misleading edges. As you can see in this illustration, if a bad guy node is surrounded by a good guy neighbors, the majority neighbors overwhelm the signal. The bad node is essentially pretended to be good because of its connections, leading to misclassification. So, how do people usually fix this? The conventional approach, which is used by the methods like GraphSmall, GraphENS, and GraphsSHA, is to simply generate more minority nodes. They synthesize fake nodes to balance the counts. But this raises a critical question. Is quantity enough? This method largely ignores the topology. We ask ourselves, are the connections between majority and minority nodes inherently harmful? And if so, shouldn't we fix the connection rather than just adding more nodes? To prove that connection matter, we conducted an empirical analysis. In this chart, the x-axis represents the percentage of majority neighbors in the minority node The y-axis is the classification accuracy. Look at the baseline methods. The graph SHA, the graph ENS, the TAM. As the percentage of the majority neighbors increase, their accuracy drops significantly. This proves the majority nodes propagate overwhelmingly, distorting information that wash out the minority signal. However, look at our method, the buffer graph, which is which is the last, the red one, represented by the red diamonds here. We maintain consistently high accuracy even when the nodes are surrounded by majority neighbors. So this leads to our solution. We adapted a less is more philosophy. Instead of generating new labeled nodes, we structurally insert unlabeled buffer nodes onto those misleading edges. Before, you can have a direct overwhelming influence on the majority node, which is gray, to the minority node, which is blue. After, we then insert the buffer node. They acts as a bottleneck or a filter. It regulates the influence, preventing the majority signal from overwhelming the minority features, while still keeping the graph connected. Here is an overview of the buffer graph framework, which operates in 3 steps. The step 1, first we pre-train a simple model to identify potential misleading edges, specifically those connecting predicted majority and minority classes, and then do insert buffer nodes. we insert buffer nodes on these edges. We zoom in on the right to show that the buffer node is created using a feature mix-up and interpolation of the two connecting nodes. And the third, we do adaptive message passing to control the information flow, which I will explain on the next slide. This is the core engine of our framework, adaptive messaging passing. The system needs to intelligently decide whether to send information through the direct path or the dampened buffered path. First, for every edge, we calculate a different score, which is S. This is based on the Manhattan distance between the predicted label distributions of the two nodes. If the score is high, it means the nodes are very dissimilar, like the majority and minority edge. Second, we adjust the direct edge weight using the formula different scores in the paper. If the scores are different, if the scores are different, which means high, the direct weight becomes low, and this forces the information to flow through the buffer path, which dampens the noise. If the nodes are similar, the direct weight stays high, preserving the natural homomorphy. To validate our work, we conducted a comprehensive experiment across 5 real-world benchmark datasets. These include Amazon Photos, Amazon Computers, the academic networks such as the co-author CS and the co-author physics, and the WikiCS datasets. Crucially, to ensure a rigorous evaluation, we standardized how we define majority and minority groups. For every dataset, we ranked all classes by the number of the nodes in the training set. We designed the top 50 of the classes as a majority group and the bottom 50 as the minority group. We compared buffer graphs against several state-of-art baselines designed for imbalanced learning, including Graph SMORE, Graph ENS, TM, and Graph SHA. How does this perform? Here we compare buffer graph against the second baselines on naturally imbalanced graph on the Amazon Computer dataset. We improved the accuracy by 1 point and 83%. We improved the balanced accuracy by 2 point and 62%. And we improved the F1 score by 1 point and 75%. We see similar consistent improvement on the co-author CS dataset as well. And we also do the stress test the model. In this chart, we artificially increase the imbalance ratio from 10 to 25, making the minority class even smaller. As you can see, all the methods degrade as the task get harder. However, the buffer graph, which is the dark blue line at the top, exhibits the most stable performance. At the most severe imbalance ratio of 25, we outperform the second baseline by about 3%. This proves our robustness. We performed an evaluation study to ensure every part of the framework is necessary. We compared the complete model, which is the dark blue, against the versions removing the different loss, which is the DL, and concrete message passing, which is showed by CMP, and update message passing, which is showed by UMP. The most significant drop happens when we move UMP, the gray bars. This confirms that the buffer node mechanism itself, updating the messages through the buffer, is the most critical component for our success. And then the parameter sensitivity. The left chart, this controls the feature mix-up for the buffer node. We found that the alpha equals 0.5 is optimal. This makes sense. A balanced mix of the two netbars creates the best buffer. And for the right chart, this is the the weight of our loss function. This performance is quite stable for the value between 0.1 and 1, showing the model is not overly sensitive to hyperparameter tuning. To summarize, our paper makes three key contributions. First, the new diagnosis. We identified that the major minority is as a key source of bias that was previously overlooked. Second, a novel framework. We proposed the buffer graph, which shifted the focus from simply counting nodes to regulating EG influence via buffers. And the third, rigorous proof. We provide both theoretical justification for the dampering effect and a comprehensive experiment showing the outperform SOTA methods. And thank you for your attention. Our code is open source and available at the GitHub link down here, and our paper is also available on the OpenView. I'm happy to take any questions.
Okay, so questions from the audience? Any questions? Let's see on Slack as well, but I think there were no questions. Okay. So I will start with one. So basically, so this approach is working on binary classes, as I can so kind of understand. So can this be applied to multi-class as well, or it just works with binary classes?
Currently, it just work on binary class, but in the future, it is the future direction on multi-class.
Okay, thanks. Other questions in the meanwhile? Okay. And one other question is, so can you see some limitations in your work, and how would you like to maybe address them in the future? Can you see them?
Okay, so currently the main limitation that we use is a fixed mix-up coefficient alpha, as the alpha equals 0.5 for all the nodes, which might not be optimal for every single local network structure. Additionally, we have only valid list on the node classification tasks. In the future, we plan to explore adaptive coefficients and the extended list to link the prediction task.
Okay, thanks. Maybe one last question is, can you see some kind of similarities between this setting and the setting where you are missing some labels from the node? So from very few nodes, can you see some similarities, and how can you address this in a similar way to what you did in this paper?
What do you mean?
I mean, I can maybe see that so this setting is quite similar, or it has some similarities with the setting where some nodes are missing the labels. Can you elaborate a little bit on that, and can you see some similarities with this setting and the setting you propose in the paper? Or it's nonsense?
Okay. Okay. I see some papers using try to reweight or removing the edges. But this paper is different because it changes the topology by turning one hop path into the two hop paths. So we create the damping effect. So the message is averaged at the buffer node.
Okay. Okay. So thank you very much. Other questions, or we can go to the second paper presentation? I guess that's fine. Okay. So thank you very much to the again. Okay then. So for the second presentation, we will have a paper on cross-domain graph anomaly detection, and it's going to be presented by Delaram. So she's here, and okay, we can start. And it's 15 minutes plus 5 of question and answer.
for being here. Today I'm excited to present our new framework for cross-domain graph anomaly detection. This framework tackles the challenge of detecting anomalous nodes in a new unseen target dataset without having access to source datasets or any labels. My name is Delaram, and this is a joint work with my advisor, Dr. Silva at Rice University. So to ground the problem, let's first ask, what does cross-domain anomaly detection in graphs look like? So assume that we have an unseen target label, and we want to detect the nodes that whose features or the connectivities look different from what is expected from that local neighborhood or the entire graph network. So just assume the social networks such as Reddit or Facebook, where we can have users that show irregular activities or abnormal connections to their surroundings. So the key challenges in the real-world problems that we are considering is first, lacking enough labels, distribution shift with the source dataset, feature heterogeneity, which basically means a feature shift with what the model has seen before, and also no access to the source data during the adaptation. There's been a lot of progress in this field, but each line of work has its own limitations. So first we have the supervised methods, which mostly rely on labeled anomalies, which is extremely rare in real world, especially when we're tackling with cross-domain problems. Then we have cross-domain GAD methods, which typically require access to the source data during the adaptation, which also raises privacy problems in real world. Then we have general cross-domain adaptation methods, which usually assume consistent label semantics, which is also not the case in anomaly detection problems. And finally, we have test time training methods, which are suitable for online adaptation, but they're typically not tailored for anomaly detection problems. So these are the gaps that we're trying to fill in our framework. So here's the exact setting of our problem. So assume that we have a source dataset with binary labels for normal and anomalous nodes, and a target dataset without any labels. And also we are assuming a set of nodes and edges for each graph. So one important note here is that we are assuming that the feature spaces are different across domains. So the overall goal is to basically detect the anomalies in the target graph using the information learned from the source dataset. And we have two important constraints in our modeling. First is that this is a completely unsupervised method. Also, this is source-free, which means that we don't have the source dataset anymore while adapting the model. So here is the overview of our framework, which is based on test time adaptation, which basically has two phases. First, the training phase on the source, and the test time adaptation on the target. So during the training, we are trying to basically pre-train our model on a labeled source dataset. So here we have a joint supervised and self-supervised loss. So first, we need to train an encoder, which basically tries to project the source dataset into a shared latent space, and also for the target. Then we have a shared decoder between source and target, and then we have a joint loss. And during the adaptation, we only need to train this encoder parameter for the target. We are reusing the encoder from the source, and here we only have the self-supervised loss because we have no labels. And about this loss, we are defining it to be the node homophily maximization, which I explain later in detail. But this is computed by taking the average similarity of the node embeddings with their neighbors. So what is the homophily for anomaly detection? So basically the key idea behind our framework is using the homophily signal as an invariant signal for anomaly detection. And what does it mean? So this is a prior knowledge that in real-world graphs, the normal nodes tend to be more similar to their surrounding neighbors compared to the anomalous nodes. And for example, in the social networks, the normal users usually form a connected tight community. But for the anomalies, this is usually not the behavior. So, which we say that they have low homophily, basically. So our method simply uses this idea in the objective function to maximize the homophily score for the connected nodes. So I'll try to go through every component of our framework. So first we have the domain-specific encoders. So as I mentioned before, we have heterogeneous feature spaces, which means that we have the feature spaces are different between the domains. So these encoders take care of that by projecting each dataset into a shared latent space. So for the source, this is going to be trained end-to-end using the labels. For the target, this is going to be trained using the homophily loss. So I mentioned the homophily maximization objective, but that also needs to be regularized because we want to suppress the noisy effect that comes from the non-homophilic connections. And by that, I mean the connections that connect a normal node to an anomaly node. So we have proposed an attention weighting mechanism which tries to make the model learn lower weights for these kind of connections. We have also put a symmetry constraint just to make sure that for each direction, we are choosing the lower weight for the non-homophilic edges. Then we have the supervised head, which is only used during the training. Which just tries to basically learn the decision boundary separating two classes for source, which is also needs to be regularized because our datasets that we are using are highly imbalanced. On average, we have less than 7% of anomalies. So we added weights into the anomalous nodes in order to make the model not ignore them by the majority class. So this is the overall loss function for the training phase, which is a sum of the supervised loss and a self-supervised loss. And this loss is basically, as I say, the proxy task for the test time adaptation, which we defined it to be the homophily maximization. So then we have the inference time. So during the inference, only the target encoder is going to be trained using the SSL objective. We are also using the decoder. We're using the decoder from the source, which makes the model being able to transfer the information from the source data while learning the new target domain patterns. So finally, we have the homophily-based self-supervised loss. So as I explained before, so it uses the idea that normal nodes tend to be similar to their neighbors. Basically, we say normal nodes are expected to have high homophily, while the anomalies are having lower homophily. So, which is going to be calculated using by average similarity of the nodes and their neighbors, which basically tries to encourage homophily consistency in the embedding space. So this is the overall formula for the objective, which includes the homophily function, also plus a regularization term, which I explained before. This is the attention weighting. So this is an overall, the overall pipeline that we used and our main contributions basically. So first we have the source encoder, which takes care of the heterogeneous feature spaces. Second, we have the attention weighting mechanism to suppress the non-homophilic edges. We have the supervised head, which learns to detect the classes in the source data. We have self-supervised objective, which is the homophily maximization. And finally, we have the test time adaptation, in which the target encoder is going to be learned using the SSL loss. So we have also, by theoretical proof, showed that each step of our training strictly increases the anomaly separation margin between the normal and anomalous nodes. And how we have defined the margin, the anomaly separation margin, this is basically the distance between the expectations of the homophily scores of the normal and anomalous nodes. We have provided a detailed proof in our paper, but this essentially just shows that the test time training with the homophily loss as the objective can provably be effective in cross-domain graph anomaly detection task. Here's our experimental setup. We have used datasets such as social networks such as Facebook, Reddit, where the users are the anomalies, like the fake users, bots, and also some review datasets such as Yelp datasets where we want to detect the fraudulent reviews. We have tried to use different sets of baselines, such as the cross-domain adaptation methods, test time training methods, and also graph anomaly detection methods, whether single domain or cross-domain. And our metrics are area under the ROC and the precision recall curve. And as you can see, so these are the data sets basically. We have a very low anomaly rate in our data sets, which shows that our data sets are highly imbalanced. This is our main results table. We have two categories: heterogeneous features, homogeneous features. Heterogeneous, which basically, as I explained, just shows the different feature spaces. And we also included some data sets that have same feature spaces but different graphs under homogeneous features. And we have tried to basically use every combinations of the data sets, like Amazon, Reddit, Amazon, like for source and target, basically every possible combination. And yeah, as you can see, we had about 8% improvement in the performance compared to the second best competing method. And one question you might ask is, what if the homophily assumption doesn't hold in the data set? Because this is basically the assumption that we made in our setting. For that, we tried to synthetically alter the homophily score of our data sets. So we started from 0.9 homophily, which is the score for the original Amazon Reddit data sets. So here's the original performance, and then I tried to decrease it. And as you can see, as we decrease it by like 0.5, the performance only slightly decreases. But after about like 0.3 and lower, the performance decreases more significantly, but still not collapsing. Which shows that in the heterogeneous cases, we still have a reasonable performance, but the ideal and the most stable performance is when we have homophilic graphs. And so by summary, we have introduced the first test time training framework for cross-domain graph anomaly detection. We don't use labels during inference, and also we have assumed that we don't have access to the source. Our objective is homophily score maximization, which uses the concept of homophily as a domain invariant signal for detection. In order to suppress the noisy effect of the non-homophilic edges, we offer using attention weighting mechanism during massive passing. And we propose using domain-specific encoders to handle the heterogeneous features. And finally, by empirical results, we showed that our model improves by about 8% compared to the competing methods. Also, we have provided theoretical proof to show that test time training can provably improve the separability between the two classes. And all right, thank you for listening. I'll be happy to take any questions.
Okay, questions from the audience? Any questions? Yes.
Hi, thanks for the great talk. Do you have a specific heuristic to determine the values of your two hyperparameters for the regularization and the self-supervised?
So yeah, for the regularizations, for the class, for the regularizer in the training part, we basically use a weighting which is proportional to the number of the anomalies, basically the anomaly rates proportion.
Some other questions from the audience? Okay, I guess there's one on Slack. So it's like asking if it could be interesting to allow the model to change the objective after the homophily is low to something like noise removal or maybe other kind of restraints. Do you have some intuitions on that?
Sure, yeah. There's definitely a lot of ways to explore for the heterophilic graphs. So as I explained, so this is an assumption of our method that the data sets are having high homophily, which is usually like a practical assumption because in real world we typically have that. But for the heterophilic cases, we can definitely use other objective functions, more tailored for the heterophilic graphs or other GNNs maybe. So, yeah.
Okay, thanks. Maybe one more question on my side. On the experimental part, so did you notice some of the cross domains which were like more challenging to address? Maybe, I don't know, some source target datasets which were more challenging.
So yeah, basically one observation that I had, like we have it in the like appendix of our paper, but not here, is that I noticed some correlation between the difference of the homophily scores of the data sets. So in the cases that we have a large gap between the data sets in terms of the being homophilic, it was more basically challenging to transfer the model.
Okay.
Yeah, that was one thing.
Okay. Some other questions? Or okay, yes.
So I'm curious about some maybe like cross-domain invariants. I know that obviously homophily was an assumption, but were there any other like assumptions that were invariant across the domains or?
So you mean as a, so yeah, basically here we have assumed the homophily like as the domain invariant signal across domains, but we can definitely like look at other settings, like for example, in the homogeneous feature setting that we have used. So we use the data sets with the same feature spaces. So this is basically like a less challenging task because there is more correlation between data sets. So yeah, I think that this is one case.
Okay. I guess we can finish now for the second talk. So thanks again to the speaker.
Thank you so much.
Okay, and we directly go to the third and last paper on community detection with graph neural networks and stochastic subblock models by William. So the floor is yours, and you have 15 minutes plus 5 minutes for the Q&A. You should maybe switch on the microphone. Oh, no, okay, let's switch now. Okay.
Great. All right. Hi, everyone. My name is Will, and today I'll be presenting differentiable community detection with graph neural networks and stochastic block models. I'll start with a quick overview and some visuals of the problem we're addressing in the paper. Then I'll get into our approach. I'll walk through some experiments, and finally, we'll have a brief discussion of the results. So So the general problem we're concerned with is unsupervised community detection, which is the task of partitioning graphs into groups based on structural and attribute information. Our approach to the problem is to combine the expressive power of GNNs with the flexibility of stochastic block models, or SBMs here. SBMs are a family of generative models commonly used to model community structure networks. At a high level, they assume that the existence of an edge between any two nodes depends only on the community membership of each. Basic SBMs are made up of a node partition denoted by Z here and a structural matrix denoted by theta. The structure matrix defines the expectation of an edge between nodes in each community. And estimating these parameters is a useful approach and a common approach for community detection. This slide is just to visualize how the basic SBM works or looks. We have a small graph with 3 nodes and 3 communities, and each node's community membership is given by the one-hot encoded matrix Z on the right here. My right, your left. The probability of an edge occurring between nodes in any of the groups is given by the structure matrix theta right next to it. The product matrix in the middle just expands the structure matrix for every possible dyad. And finally on the right, we have the adjacency matrix of a graph generated by this SBM, which is just independent samples from a Bernoulli. Moving on now to the more specific task of community detection using neural networks, which we'll refer to as deep community detection. In the past, neural networks have been used for community detection and similar tasks through the implementation of graph coarsening or pooling, link prediction, modularity maximization, and other techniques adapted to neural networks. For the focus of our paper, we're just considering loss functions. To that end, special training routines and custom neural network architectures are not considered in our work. The goal is to just have a loss function that can be integrated into any deep learning framework. So to pursue this goal, we turn to SBMs, like the title suggests. And while there's been work in the past on integrating SBMs in deep learning, ours differs in that it's focused on adapting the SBM likelihood functions into neural network loss functions. And we do this in such a way that the loss function is differentiable with respect to node embeddings from an arbitrary neural network, and so that the model can be trained with simple forward and backward passes. So how do we actually do this? We'll start with some preliminaries in notation. We have our graph, script G, our adjacency matrix, which we assume is binary valued for now and not necessarily symmetric. And our partition matrix Z, as I said earlier, it's a one-hot encoding of each node's community membership, and the structure matrix theta, which was defined earlier as well. Now, a standard formulation for the SBM assumes that the number of edges between any two nodes is Poisson distributed, conditionally on their community memberships. The log likelihood for this assumption is given in equation 2. A quick note, I did say we're dealing with binary valued adjacency matrix, so this equation 2 is actually a partial log likelihood. Another formulation assumes that edges are Bernoulli distributed instead, which aligns better with our definitions, and that log likelihood is given in 4. Now we have our first useful variant, which is the degree corrected SBM. And this introduces a new parameter phi, which adjusts for each node's degree. And this is useful because real-world networks exhibit sometimes quite significant skew in degree distribution. So correcting for that in our likelihood is an important feature. And we can implement degree correction for either our Poisson or our Bernoulli models. And we do both in this paper. And then the final variant worth mentioning for our context is the overlapping SBM, which allows nodes to be members of more than one community at once. And for this, we use P instead of Z to define the partition. And rather than a one-hot encoding, the rows of P can be thought of as the frequency with which each node is in each community. Now, how do we estimate all these parameters for our SBM? Well, the structure matrix is fairly simple. It's just the maximum likelihood estimate, which has this nice closed form solution in equation 3. That's actually the same for both the Bernoulli and the Poisson variance. And then the degree correction parameter for the degree corrected SPM also has a closed form solution here in equation 6. Now, the partition matrix is a bit more difficult to estimate. It doesn't have a closed form solution, so it could be found combinatorically, but this is often far too computationally expensive, especially on large real-world graphs. Common approaches for estimating it include MCMC algorithms or variational Bayes methods. In this paper, though, we predict a soft partition matrix P using a graph neural network. And then to get the structure matrix, we simply just plug that output from the neural network into the MLE from the previous slide. And then these estimates are plugged into the negative log likelihood of the SPM, and we call that J, and the model can be trained on this as a loss function with any optimizer like Atom. We use Atom optimization in our paper. And a quick note here, equation 9 is our loss function. In the last line, we have summations over P sub E and P sub N. Those are just samplings over the positive and negative edge sets respectively. Doing negative sampling in this way, it's useful for sparse graphs where the negative edge set is much larger than the positive edge set. And you'll notice that equation 9 is an adaptation of our Bernoulli model, but it's easily modified to accommodate the Poisson model or for the degree corrected variance. And with this, we have a set of loss functions derived from SPMs, which are fully differentiable with respect to the neural network parameters. Now, it should be noted that these likelihood-based functions can be expensive to compute for large graphs. So it would be nice if we had a loss function that exploits the sparsity of the adjacency matrix to speed up computation. And this motivates our adaptation of graph matching. Graph matching refers to the task of identifying a correspondence or an alignment of nodes and edges across two graphs. Now, for our purposes, we define a graph G sub theta, which is the weighted graph induced by the structure matrix that generates G. And each node in G theta is a supernode corresponding to a community over the nodes of G. And the correspondence between G and G theta is simply defined by the partition matrix. In the graph matching setting, the correspondence matrix is unknown, so Z must be found by solving this quadratic assignment problem here in equation 14. Another issue for our SPM setting is that the structure matrix is unknown. So we have to substitute our MLE for theta into the quadratic assignment problem. And so doing this, we can use our graph neural network again to predict the partition matrix, and we end up with this new loss function in equation 15. And what's good about this loss function is that it should offer us an improvement in speed over the likelihood-based functions, as it's computationally reliant on sparse matrix operations. So far, I've described a few ideas. First, the SPM likelihood-based loss functions, which we have the variance for the Poisson, Bernoulli, and the degree-corrected models. We also have the graph matching-based loss function. And now the last thing I want to introduce is the regularization term. And this regularizer is meant to do two things. First, it penalizes structure matrices that do not generate assortative graphs, graphs that are more connected within communities and across communities. And secondly, it encourages the model to distribute the partition across enough communities. And now this penalty term in equation 16, it's simply the distance of the structure matrix diagonal from unity. So those are the methods. Now it's time to evaluate them. Our proposed loss functions are tested on both synthetic and real-world data sets, which include both overlapping and non-overlapping community structures. training is carried out on a node-induced subgraph, then testing is done on nodes from a holdout set, which makes the evaluation transductive. And to measure performance, we use normalized mutual information and pairwise F1. And we include a number of comparison approaches. And it's important now to reiterate here that we're just concerned with loss functions, not with custom architectures or training routines. So for that reason, we only compare against loss functions that can be separated from the rest of their original framework. And we just use a standard GNN and a standard optimization routine for all experiments. The synthetic graphs we evaluate on are generated by SBMs with different numbers of communities. We have 4 standard SBMs and 4 overlapping SBMs. And the real-world graphs we evaluate on are just some popular benchmark data sets, which include the Microsoft Academic Graph, which has overlapping communities. And because the true number of communities might not be known in practice, we fix the output dimension of the GNNs to be 25 for all our data sets. So here are the synthetic results. On the left, my right, your left, is graphs with disjoint communities, and on the right are the graphs with overlapping communities. These results are averaged over 10 random initializations, and the SBM losses that we proposed are highlighted in the bottom 5 rows here of each table. In general, we see that the SBM loss functions outperform or do just as well as the comparison approaches. There's a lot going on in this figure. I included it just to demonstrate the difference in speed between the edge sampling approaches and the matrix sparsity approaches. We can ignore the different shapes and colors and just notice that between the 2 classes, they perform similarly in terms of normalized mutual info. But the loss functions that use sparse matrix operations, which are on the left side, and those include our graph matching loss, those perform much faster. Seconds per epoch, that is. And here are the results on real-world datasets. Again, on the left are the graphs with disjoint communities, and on the right, we have the overlapping communities. Scores, you'll notice, are not as high across the board, but in general, our SBM loss functions outperform or do just as well as the comparison approaches. And again, this figure shows the speed between the 2 classes of loss functions. And again, we see that the loss functions that use sparse matrix operations are much faster than the edge sampling approaches. And before we wrap up, I'll just add a few comments about these results. So as we saw, the SBM loss functions, they do very well, just as well or even better than some of the comparison approaches. Furthermore, like we intended, the graph matching approach does outperform the edge sampling approaches in speed. And this was true for the comparison approaches, which the comparison approaches we included, which use sparse matrix operations as well. An example of that would be the deep modularity network, DMON. There's more about that in the paper. And additionally, as I pointed out, the performance, well, I didn't point it out yet, the performance on the overlapping graphs with overlapping community structure was lower across the board. And this appears to be a common problem across all the approaches we compared, and it likely just means that overlapping community detection, this is probably well known, is a much more difficult setting. In the future, more work will be done to try and adapt the overlapping and the mixed membership SBMs in order to improve performance on overlapping data sets. And additionally, we'd like to explore more stable estimates of the structure matrix, as the MLE is shown to be unstable when community sizes are small. I think this paper offers another interesting path forward for unsupervised community detection with graph neural networks. It's also a good jumping off point for simple integrations of neural networks and SBMs, and it's indeed something that we're excited to be exploring over at Lighthouse. Thank you.
Questions?
Thanks for the presentation. So I have a very quick question. Maybe you covered it in the talk, but so when you try to estimate the trace, you calculate the trace in the matching loss. Do you use some like randomized algorithm to do that, or you just like calculate it? It has some properties.
I'll go back to that equation.
Yes,
Here.
this one.
So are we looking at 15?
Yes.
That's just more or less straightforward matrix
Traces.
operations.
Okay.
We can break up the left two terms and the right two terms. So you have a sparse matrix times a sparse matrix, and then you have a smaller dense matrix times sorry, I misspoke. It's a sparse matrix times a dense matrix. That's your first operation. Then you have a smaller dense matrix times another dense matrix.
Okay.
And you don't need to take the full trace from that. You can just basically do element-wise multiplication and then row-wise sum.
Okay. 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 Yeah. Thank you.
Other questions? Yes.
So one question is about the assumption that the graph follows an SBM model. Like SBM is a very big simplification of like what real graphs look like. So why do you think this works? That like assuming that for instance, each partition is like a random graph is effective when you apply this to like in real data sets? And maybe another question also is, how do you compute the loss? It seems like it's n square. You have to account for every pair of nodes, whether they are connected or not. But you have like some way to optimize that.
Yeah, sure. So the first question, the assumption of a graph is generated by an SBM. Sure, yes, that is a somewhat strong assumption. Certainly not all graphs will be generated that way. I think SBMs are known to do poorly in describing real world graphs, and one of the purposes of the degree corrected SBM is to address that. Instead of assuming that nodes within the same community have stochastically equivalent degrees, the degree corrected SBM allows for some sink or source nodes. Some nodes that have much larger degree, which is more common in real world networks. But I agree with you. It is a strong assumption, and it's something that should be explored more. And then the second question was about the sum of these elements in the matrix, or in the adjacency matrix. So yes, to sum up over every single element of the adjacency matrix would be expensive, which is why we have this negative sampling approach. You can take a sum over all the positive elements and then take a negative sample over the negative or the non-existing edges, which is what we do. And then that also leads to this graph matching approach.
Okay, yes, there's another question.
So for cases where your communities aren't overlapping, don't the conditions you have on Z here mean that Z is going to be orthogonal, and maybe your Frobenius norm there simplifies in that case?
So in this formulation that we have for 14, right, we have the Z is only 0 or 1, right? But when it's a neural network, we have Z is definitely not guaranteed to be 0 or 1. So yeah, it's an approximation. This works when you have when you have Z is 0 or 1, but it doesn't necessarily work when Z is not 0 or 1. That's why I should have made that more clear. But yes, it's an approximation when you use your P from your neural network. But it seems to work in the experiments pretty well, so we're content with it.
maybe one last question, and then we'll close the session.
So in the experiments you showed, you compared against other loss functions. So that was only deep learning based approaches, I guess. Have you also compared against regular SBM community detection?
That's a great question. So we kind of defined a quite narrow scope for this paper, which is just we want a sum loss function that can be used to train any end-to-end neural network. So that would exclude, standard approaches for estimating an SVM. But that would be an interesting investigation, but it's out of scope for us.
Okay, I guess so. So that's it. So thanks again to the speaker and to all the speakers who attended. And that concludes the oral session. And now we will get to the tutorial on Graph Foundation models. Thank you.
Okay, so while our tutorial organizers is setting up, we can take a 5 minute break.
Okay, great. Hello, everyone. So my name is Ben, and alongside with Xingyue and Zifang, which is online, we're gonna give out this tutorial. So thank you for having us. Both me and Xingyue are PhD students from Oxford, and Zifeng is a postdoc for Cambridge. So we all come from UK. So luckily we've avoided the jet lag thanks to NeurIPS. But this tutorial is going to be partitioned into three. I'm going to talk mostly about node-based tasks, whereas Xingyue is going to focus on knowledge graphs, and Zifeng is going to finish it off with LLMs that everybody knows and loves. So my bit is going to take around 50 minutes. Then you're going to have a short break because I've heard you like breaks, and then Xingyue is going to take it off. Okay. Cool. So let's start with part one. I'm going to take questions at the end. And then we're also going to have a very short kind of Colab notebook, which is already uploaded. You can go ahead and play with it if you fancy. Luckily, it also runs. Okay, awesome. So let's start graph foundation models for node-based tasks. So this is not going to be an overview over different works. It's mainly the contents are going to be kind of a motivation because the field of, or like the kind of trial and error of making foundation models for node-based tasks, it's still kind of in the baby phase. It's very much at the start and the beginning. So I'm going to talk about some motivation. Why do we care? What's the setup? Because it's slightly different than just having a GNN and applying it different, like the same GNN over different data sets. Then I'm going to slightly discuss about the history, about how kind of theoretically these GNNs came to be. And kind of try to copy this trend and move it forward to graph foundation models and how I expect them to develop or how I hope they can be developed. And then some experiments and some maybe, I don't know, promising future directions. Okay, so let's start with some motivation, okay? So first motivation is efficiency, okay? So up to now, we've been training, all of us been training GNNs, right? And we have kind of our really nice data sets, CoreCiter and PubMed, which everybody absolutely hates. And so we train a GNN per data set, but that cannot go longer in 2026, at least to my personal perspective. Okay, some companies even train a new GNN every day or a new GNN like twice a day. So this is very inefficient. And so having one model, kind of a large graph model, would be super, super nice and a nice solution. So that's one motivation. The second motivation would be knowledge transfer. So take, for example, two completely separate domains. One of them would be social networks, and the other would be road networks. They both share some underlying kind of concepts. For example, the influence of highly connected nodes is of importance. So in social networks, these would be influences which kind of carry value in this graph and have some strong importance. Whereas in road networks, junctions which have lots of connections to them, right? Lots of roads can kind of lead to traffic jams and could affect prediction and the traffic flow. So high degree nodes are of importance, right? So that's kind of shared across different domains. So there are many other such properties. And the last motivation I'm going to give out is that, of course, there's a little bit of hype in foundation models, okay? And with kind of how LLMs have started revolutionizing the world, I hope and expect that GFMs maybe, possibly, if all of us work on it together, can do the same. Awesome. So the first work that kind of came out to try to do this is called Graphene, okay, which showed us a new hope, okay, in essentially training a specific architecture over one data set, let's say Cora for the sake of the argument, and then was able to test its zero-shot performance across 30 other data sets, showing that it's able to kind of generalize and capture some semantic and some meaning, which is a very good and very good starting position. So some models like that have shown promise. It's been published in ICLR and in Singapore. However, there are some cons, much like to any work. There aren't many theoretical guarantees to this work. And more importantly, is that the architecture itself is vastly different than the GNNs we know and love today. So what I would hope to kind of achieve is a way to kind of lift all the GNN research that's been done and that everybody kind of worked and derived their favorite GNNs, right? Some tailored for homophilic, heterophilic tasks and vice versa, and to see if that could be lifted and leveraged into architectures that can train across different data sets, right? So like one model that can accept as input varying amount of features, varying amount of labels, okay? So awesome. So now the question came to be, how can we derive these GFMs without having I don't know, a tail, like with having lifting GNNs into these GFMs. And so there's an interesting work just presented in Europe. And for the sake of this discussion, we're going to focus on node classification, but the same applies for node regression. And a little bit of spoiler, you're able to lift your favorite GNNs, let's say mean GNN, GUT, SGC, GCN, GCN2, or whichever GNN you guys have worked and developed over the years, and you can make it foundational in the sense that you can train it on one data set and test it on multiple others. Okay, so first of all, let's talk about the setup and define it slightly more thoroughly, because I've mentioned multiple times that you train it on one data and test it on multiple others. So what do I mean by that exactly? So let's imagine that I have this magic box and I kind of poofed it into existence, that we now have a graph foundation model that's able to accept as input, our features and give us meaningful prediction. Nice, cool. So we used from the kind of GNN realm that the GNNs accept features, the feature matrix, and spit out predictions. If that was the same case for graph foundation models, then let's look at the first row where we have some sort of feature matrix and then some sort of prediction as an output. Awesome, great. Now, if I kind of secretly permuted the labels, right, and I swapped the tag onto label 1 and label 2 and just swapped between them, okay, and reran my model on the same feature matrix, okay, then the output would have been completely wrong because they swapped the labels between 1 and 2, right? So instead of getting 100%, if it's a binary classification, 100% accuracy because my GFM is so good, all of a sudden I would get 0, right? So that kind of tells us that labels or some partial label information needs to also come as input, which is different to the kind of GNN setup. Okay, it starts to kind of resemble more in-context learning. Okay, so some label information needs to be part of the input for us to, have some meaning to what it means to be class 1 or class 2. Because now, if we just swap class 1 with class 2, we swap the labels, then the prediction as well, the labels will be swapped. Okay, so that's a kind of important point to make. This is why it's important to detail this setup. Because conversely to GNNs, labels now are part of the input, okay? Awesome, great. So how do we kind of denote this task? We call it label in painting. Again, this is a subtask of a task of in-context learning, because again, labels are part of the input, right? So we have, for example, we have a subset of the nodes called L, and the subset has known labels, and we're trying to in-paint, much like in computer vision, when you have a part of the picture and you're trying to fill in the rest of the picture, we're trying to in-paint the rest of the graph classes. So in this case, we have a binary task of blue and red, and the rest of the nodes are unknown, and so we're trying to predict and in-paint the rest. This could be very similar to what most of you know as label propagation, where you could have the same running example here of blue and red, and usually this blue classes start propagating and the red classes start propagating. But because we use a label propagation is not a learnable algorithm, right? It's more of a heuristic. In label in painting, you could have examples where, since you're also utilizing features for every node, then the class of a node that's surrounded with blue nodes is not necessarily blue, because the features themselves could correlate better with red, right? But the task itself is the same. It's labeled in painting. You have some sort of the colors in this graph, and you're trying to in-paint the rest. Again, very similar to in-context learning. Great. So another nice point about label in painting is that you can train a model on a certain graph with X amount of classes, and then in zero-shot prediction, it doesn't matter how many classes you have, you're just trying to in-paint given partial information. So the colors can vary. That means now in the zero-shot performance, in the zero-shot in the test time, we can have more classes, less classes, and the model would learn how to best in-paint given the amount of classes that are given as input, right? So that's the kind of, again, the important note of the labels being part of the input, because now this model is able to, this task is able to process varying amount of classes. Okay, so in order for us to kind of discuss graph foundation models and how one would expect them to be derived, let's first discuss GNNs and how kind of, at least from mathematical first principles, how they occurred or came to be. Awesome. I'm gonna focus on four kind of steps. One is understanding the data. This is okay. The bug with this microphone. Hello, hello. Okay, I'm gonna try to continue on, okay, for the sake of the time, but my voice might fluctuate a bit, I think. Do you guys have another microphone? Or is it like a battery issue? Or I think it's working now. Yeah, I think it's fine. Okay. Okay, great. So Zifeng might not like this picture because he's all for LLMs, but I'm still trying to salvage and utilize all the GNN research that's been done. So the way that we're gonna tell the story of GNNs is we're gonna start with analyzing the symmetries, move onward to deriving the layers, and then afterwards, usually after some mathematics, I think it, no? It survived again. Is it best if I stop or should I continue like that? You can use this mic. Just a moment. Hello, hello. Awesome. Thank you for bearing with me, or with this. Cool. So again, understanding the symmetries of the data, deriving the linear layers, then we're gonna sprinkle some non-linearities, much like what we like to do in machine learning. Then mathematicians, enslave for us and prove universality, which is always nice. And then, because everything has been designed for sets, we're gonna move this into kind of graphs. So let's see how that correlates to GNN research. So first of all, the symmetry that we care about, permutation equivariance, okay? So if we all know this by heart already at this point, if we kind of reorder the order of the indices of the nodes, then whichever function we apply, right, could commute with this reordering, with this permutation, and this is one of the symmetries that we kind of care for and we know that our data should abide by. Great. As a result, a long time ago in a land far away, deep sets came out, right, and kind of derived these linear layers that work with the symmetries. So there are two linear layers, as you can see below. One of them is just a completely regular linear layer, and the second is essentially a global pooling, some sort of sum pooling across all the features in the set. Okay, we're still in sets. Only in bullet point 4, we're moving to kind of the graph domain. Awesome. Now, in addition, there's also the proof for universality. We show that this can approximate any function. Nice, great. And then how powerful are graph neural networks, GNN, or any other one of the kind of pioneering GNN papers essentially changed the global pooling into some local pooling. Okay, so the summation of features across the whole graph instead has been swapped with local aggregations. So each node has a summation or some sort of aggregation across the one hop local neighbors. Okay, so the process is recognizing the symmetries. That's step 1. Step 2, deriving linear layers. Step 3 is very nice kind of universality. And step 4 is swapping the global aggregation into a local one. So let's see if we can follow the same kind of train of thought for GFMs, and maybe we can have like some sort of recipe that we can follow and lift GNNs or use the same kind of train of thought for GNNs just for GFMs. Okay, so back at it again. Now let's understand our symmetries. We've already kind of detailed that our inputs also include the labels, right? So partial amount of labels. But now, in addition to the node equivalence, permutation equivalence, we have 2 other symmetries. And those symmetries are the following. The first one would be feature permutation invariance. So since our input includes the feature matrix and the label matrix, however, the output includes only predictions, then if we change and reorder the order of the features, that should not affect our output prediction in a graph foundation model. Okay, so that's an additional symmetry which has been added. And the last one would be label permutation equivalence, which correlates to my earlier example saying that if I change the labels of two classes, then the prediction should change accordingly. We'd expect it to change accordingly. Great, so here instead of just 1 symmetry, we have 3. So if beforehand we had deep sets which took care and derived the linear layers for one of the symmetries, we're lucky enough to have another very interesting paper from 2020, I think, which got an outstanding award. I also recall ICLR, might be incorrect there, which added the additional symmetry of feature permutation equivalence in addition to node permutation equivalence. So that already derived the linear layers for that. And the most interesting part about it is that it uses tensors instead of matrices. Now, this might come in as a surprise, but it's actually very intuitive. And the reason is as follows. Let's look at deep sets for a second. We're going to retract back. So in deep sets, the learnable layers are applied over the feature axis, right? However, that kind of fixes the number of features that we expect as input. Now, if we would like to add another symmetry, right, over said features, we can no longer apply this weighted matrix over the feature matrix. Another way to think about it is that if, for example, I would want to apply a weighted matrix on the node axis here, we all would say, of course, one cannot do that, right? Because that would fix the size of the graph, and you cannot multiply a learnable matrix to the left. The same would apply with this work. Once you try to include the feature permutation equivalence, you can no longer apply a learnable weighted matrix to the right. So now, both the node axis and the feature axis get this interesting treatment where we try to respect the symmetries, and we can no longer apply a weighted matrix not to the first axis or the second. So we're slightly stuck. And the kind of out-of-the-box thinking would result in, okay, we'll have to create a third dimension under which we can do the machine learning part. We can apply the weighted matrices and sprinkle some non-linearities on top of it. And this is why, essentially, they lift it from 2D matrices to 3D tensors. And I think that's one of the most important key details, I would say, in this kind of derivation and for GFMs. Yeah. So now you have three axes. Usually your input would be of dimension n by f by 1, and then you lift, and then you walk on this one axis as a hidden dimension. And another kind of interesting detail is that if beforehand you had a pooling over the nodes in deep sets, here you also have some sort of pooling over the features, because we have this interesting new symmetry, and that includes new linear layers. So you also have a kind of global sense of what it means to kind of have the summation of all features. And now back into the graph foundation model setup, where we have three symmetries, and we need to also account for label permutation equivalence. Here things become slightly even more hectic, and you have an additional input, which is the label matrix, which also has to be lifted into a tensor. So you have two tensors this time that you play around with, the one in green and the one in blue. And you work on the third dimension of each. And as a result, you get some more additional poolings. Some of them you recognize already. It's the pooling over the nodes, the pooling over the features, pooling over the classes. And the one that's with the kind of bubble shape, I find to be the most interesting. It's essentially summing all the features and transforming that information into the label tensor, or doing the opposite direction, summing all the class information and passing that into the feature tensor. And the nicest thing about this, and the reason I'm showing you this, is because now you can swap the pooling over the nodes and change that into whichever aggregation you like. Much like I've discussed beforehand for the deep sets example, right? We had this kind of transformation from a set example into the graph domain, where we change the global poolings into local one. Here, one can follow the same route, take these linear layers which have all kinds of different poolings, some of the features, some of the labels, those would be retained. However, all the poolings across the nodes, you can change them into local GNN aggregations, and then your model, your favorite GNN, can work as a graph foundation model. It can work on varying data sets, varying feature sets, and varying label sets. So in a nutshell, you select a GNN, you apply these linear layers, these TS nets, swap the dense operator of the 1NN with whichever aggregation you have, sprinkle some linear layers, and sprinkle some non-linear layers in between, and your backbone can now, if you follow the setting where the label is your input, then your backbone can now work on varying datasets. And some experiments to show that. These experiments show that you can transform any GNN architecture into a GFM, and these GFMs kind of benefit from knowledge transfer. They can do zero-shot prediction, and they can be essentially applied to any data set. So all the previous GNN research has not been lost. We test this and we show this with around 30 different data sets, varying domains, and have some efficient Triton code that has at least 5 different models that you can test and play with. I'm also going to show an example in Colab in a moment's time. And the interesting bit is that, as you can see, let's just jump to this one. You can see here, this is the original kind of result slides I've already shown. You can train mean GNN, GOT, SGC, whichever GNN you want. Just make sure you use the linear layers and the tensor representation instead of a 2-dimensional matrix. You work with tensors instead, and you're able to make this into a GFM. You can train it on Cora, and test it on a bunch of, or train it on whichever dataset you fancy, and train it on a bunch of others. And then And the last kind of experiment that to me is the most interesting one is that there have been some results showing that if you train on more graphs, performance increases. Yes, the increase in performance is relatively small, but that's due to the size of the datasets used and due to the amount of training examples exhibited. The training examples here are up to 200 nodes, 300 nodes, not too many. And so the increase in performance is very small because it's also over 30 different data sets and benchmarks. But this kind of shows a promise, and maybe future scaling could be in the making. So if somebody took this further, one could probably extend this graph and maybe show if it keeps on increasing. This kind of methodology can be extended to tabular data, to relational deep learning, even to knowledge graphs, analyzing the symmetries, following this in-context learning setup, and trying to kind of derive the layers for different domains, or extending this to kind of other tasks besides the node-based tasks. Here you have some details of the paper specifically and generally more on this work. And I think I'll take some questions now. And then we're going to have a Colab notebook in which I'm going to show you how to kind of implement this and transform your GNN into a GFM. Any questions from the audience or Slack? I don't have access to Slack, so I'm not able to see. No questions on Slack. Go ahead.
Thanks for the walkthrough. Just wanted to say that before our paper, there was a paper by Siamak Ravanbaksh group learning on, I don't remember the name, but it's from ICML 2018, and they did sets of sets, which is essentially the setup that you have here. We kind of generalized it. So yeah, I just wanted to give them a bit of the credit that you gave us.
Yeah, that's a great comment. So there are multiple other works that I could have mentioned, but my kind of intent with this was to kind of give everybody access or intuition as to how to move from the regular GNN setup in which you train a model per dataset, and how can each person take this further and take the research and try to make it more foundational in a sense. So there might be, there probably are many other works that I haven't mentioned. The intent here wasn't to mention all the works, so, but thank you for the comment. That's very great. Any other questions, remarks?
Yeah, thank you. Very cool work. Maybe I missed it, but you kind of make the argument that you can plug and play any architecture or setup that you like. But if I looked at the performance, pretty much every kind of fancier architecture goes and sucks more and more. So doesn't that kind of defeat that point?
So that's a great point to be made. So I'm not sure if I would necessarily say that fancier architectures work worse, but you can see a slight difference between like GUT performs worse than mean, and then GCN2 performs very badly. It's interesting to see, some GNNs that are specific to maybe heterophilic graphs would perform generally bad on all the graph domains, right? It could be that they're so tailored to heterophilic graphs that, that's the domain in which they would work on. Yeah, that could be the case.
Because in this graph, my intuition was that GAT was going to be the best by far, but it's not.
I expected that as well, I'll be honest. It could also be a function of the training data, because here I just trained in Cora, and imagine you're training on a very homophilic data and testing it on a very wide range of different domains, heterophilic, homophilic, with varying sizes. So a more thorough experimental kind of analysis is in order, I think, to be able to derive some conclusions. Maybe simpler is better. I don't know. It could be.
Okay, cheers.
A good point.
Okay, so there's another question from the Slack, asked by Rafael Artinano. I'm just gonna read it out to honor the original question. So one question, the permutations of labels and in features should be equal or of the same type. So that's the first question.
Can you repeat it? Sorry.
So I guess okay, one question, the permutations of labels and in features, should they be equal or of the same type?
I'm not sure what do they mean by
Yes,
equal?
that's what I'm sure about. Okay, so I probably would ask a second question while that person is typing in. The other question would be if the variation of hyperparameters between data sets hurt.
So that's a good point. And again, I'll be quite frank. I think the amount of experiments done here is, since each kind of inference time takes a while because it's over 30 data sets, the size of the hyperparameter grid isn't very large. And so if you train on different data sets, you get significantly different performance. So if you train on Quora or if you train on Roman Empire, the kind of inference performance varies significantly. So hyperparameters are also a big influence. So yeah, they would be a big influence. That's the question.
Okay, so the clarification from the person, the first question is that whether they should be permuted equally, like whether the labels and in features should be permuted equally.
So whether the labels and the features should be permuted equally?
And in features.
And in features, you mean? Okay, so the permutation between the labels and the features could be completely different. They're kind of on a spread axis. Same as you would expect of the node indices, right? They can be permuted as you like. I think if last chance for questions, if there are none, we'll move to the kind of Colab portion. And then once that's done, Shigeru would take over and kind of talk a bit more about knowledge graphs. But my intent here is that I hope people can kind of leverage this 3D representation, this tensor representation, and extend the GNNs into GFMs, because we can all move forward from this point and work in a more foundational setting. Okay, awesome. So I'll just move to the Colab if that's fine. So the Colab should be already online for everybody. And we can kind of, and I don't think I'll have enough time to go over the whole Colab, but I kind of made sure that you have a lot of content and material. And the Colab is going to be partitioned as follows. We're going to have an example implementation for deep sets for symmetric elements, which is the two symmetry incorporation, and for TSNets, which include the triple symmetry. We're going to validate that all the symmetries are enforced by these architectures. Okay, that's the first part. That's the first section. And then following onwards, the last section is essentially training a kind of triple symmetry, one that incorporates the three symmetries I discussed before, a GNN like that, which is essentially becomes a GFM. And then you can just swap the GNN backbone to whichever GNN you guys want to work with. Okay, so for the sake of kind of the time limits, we'll mostly focus on the first bit, which is validating that we have the equivariance symmetry nailed out for all of the three basic papers, which is deep sets for symmetric elements, and the triple symmetry. Great. Again, this is all on the website, so you can download this and run it. Great. So let's start. First, it's a couple of prerequisites. I'm gonna skip that. Labeling painting. Yeah. Should I wait a bit for people to download this, or?
The link to the lab materials has been posted on our website. If you can go to the program tab, and then under that tab, you can go to tutorials and scroll down to the second tutorial. There should be a link which directs you to a GitHub repo. and you could download the Jupyter Notebook from there, and I think you would need to launch a Google Colab runtime yourself. I think we could wait for a few minutes for interested audience to set it up.
I think that in the meanwhile, I can just keep going, I guess. Yeah. Okay. I'll just keep going with the example and go and do a bit of a walkthrough through the code until time cuts me through. So we've discussed the labeling painting setup and the task itself. But again, the most important bit is that we have both features and partial labels and input. And now in this notebook, we're going to validate equivariance. I made sure that it's written in detail, the definition of equivariance for everybody to see and also go through it. We've detailed the symmetries of the data that we have, the triple symmetry. So it's three symmetries we're going to enforce. So we're going to go over this part 2 now. Part 1 is mainly an introduction and some material for you to read if you want to go over things again. So the implementation of deep sets. So in the code here, we're going to have just 2 learnable weights because we have 2 linear layers, right? And the first one is going to be some global aggregation. So essentially a summation over all of the nodes. It's not really nodes, it's elements because we're still in the setup, right? Which is then a weighted linear layer is applied afterwards. And then the second linear layer is just a simple regular linear layer. So that's the basic deep set implementation we all know and hopefully love, right? So that's the one we followed through here in this cell. The next one is deep sets for symmetric elements. Here we're going to have now four linear layers. And the more important bit is that we're going to have a tensor representation instead of a matrix, right? So we need to keep track of the correct dimensions. We're going to have some input channel and some output channel. So 4 different learnable weights with some bias as well, of course. And here, to simplify things and make them slightly more intuitive, we're going to use ISOM instead of using matrix multiplication, just to make sure we keep track of the right dimensions for these learnable weights. And then the first term, as you can see, has double pooling. It has both pooling over the features and pooling over the nodes. So in this case, we choose mean pooling, but any pooling or any aggregation can be used. The second term has only pooling over the nodes. The third one has only one over the features. And the last one is just a regular linear layer, so nothing needs to be done. Okay? So the important bit is just to keep track that we're using tensors and to make sure we're using ISOM correctly to be able to incorporate all the linear layers. Now, lastly is the part where we have the triple symmetry network. And here I started already detailing how an aggregation would look like in the graph setting, although we're still in the set one. So it's slightly more complex, as you can see. But here, instead of just the regular linear layers, we're going to have some graph conv. Okay, so this can be swapped to whichever graph convolution or whichever local aggregation you want to enforce. So instead you just swap these 6 lines here to your regular GNN and make sure that it's able to work on tensors. Okay, and there's some more additional details, but essentially by just swapping these 6 layers, this layer here, the equivariant layer, is going to do the rest of the pooling that has been described in the slides beforehand for you. The rest of the code is as follows. And if you run the permutation testing, you see that, you would see that the DSS layer is, sorry, it should start with deep sets. Yeah, so the deep set layer is SN equivariant, but not equivalent to the rest. the DSS would be SN-SF equivalent, but not equivalent to SE. And the final equivalence test for the equivlair is equivalent to all of them. And I think that I'll cut it for now so there's enough time for Xingyue and Zifeng. Yeah, and I don't think we have enough time to take questions for the Colab one, but there's significantly more content and material I just wanted you to have access to. So everything is there with instructions and additional details. Most important bit is that you can swap your GNN in this block over here and just use it as a kind of, just use it as you please to have a GFM in this part. Yeah. Sorry. Maybe we should have a 5-minute break in between. Yeah, I heard that's a good idea, so let's implement that. Yeah, thank you, everybody.
All right, so we are about to start the second part. And I think what I would just hand it over to our organizer to.
Hello? Hello, can you hear me? Okay, so we're gonna start the second part of the tutorial, which is about knowledge graph foundation models. And yeah, I guess I'll just start. Oh, so by the way, I'm Xingyue, and I'm currently a PhD student in University of Oxford. And my basically interest is knowledge graph foundation model. No surprise. Okay, so here's the outlook of the talk, and also there will gonna be another set of tutorial happening right after the talk, before the question answering. So feel free to ask questions after the talk. So essentially, we're gonna look into 5 parts. First, we're gonna introduce you guys what is knowledge graph foundation model and how is it different from the traditional graph foundation model. Then I'm gonna talk about the expressivity of KGFM, which is the recent work we've been submitting to SAML. The third one, we're gonna talk about something called stochastic KGFM. It's a work, it's ongoing work, and we're trying to talk about how they're different from the traditional one and whether they're good or not. Like, we don't know, but let's see. And then fourth, I'm gonna mention about the other KGFM that I haven't mentioned in the fields. And it's really like some inspiring work, and I think we'll have to include them there. So this talk's not gonna be one work, it's gonna be like multiple works spanning across the whole kind of area. And it's like a brief introduction of the whole KGFM communities. And finally, I'm gonna talk about how to extend the knowledge graph into knowledge hypergraph, in which case instead of having binary entities, you can have, binary relations, you can have multiple arity relations and still construct a foundation model out of it. So yeah, let's get started. So here's some Nano Banana works that I have to credit. So essentially, what a knowledge graph foundation model? So it's a foundation model that specifically trains on, it carries out inductive link prediction on knowledge graph. And this basically means that once you train this model, you can apply to any, any knowledge graph with any nodes and any kind of relation types. And we're gonna introduce that later, like specifically how that means. And it's essentially there's only one question we want to solve. Traditional GNNs already can do this like node inductive task. So giving a new graph, if you have new nodes, the traditional GNNs can already learn the node embedding like during the testing by doing aggregation and message passing. But traditional, like there's a lot of way to do GNNs on knowledge graph. So here, but knowledge graph, it means a graph that is directed. And there's a set of relations such that each edges corresponds to one relation. And I'm gonna show an example later after the slides, so bear with me, please. And essentially, traditional GNNs for knowledge graph are something called relational message passing neural network that we have characterized before. And the idea here is always, because you have like additional information on the edges, which is relation type, most people are just, oh, let's take a relation ID, let's take a relation embeddings. We learn over that, and this is gonna be our things to be applied during the training time. And there isn't really a good way to learn over this relation like ID on the fly when you have a testing, like a new testing graph. So that's why traditional GNNs on KG, RGCN, CompGCN, or even NBFNet, they can only apply and train and apply on the same graph that kind of like have the same relation type, but they cannot do that across different relation type. Thus, they cannot be a foundation model, because if you have any like kind of like new graph in the different domains with different kind of relations, then you cannot really do any prediction over it. So here, the idea of knowledge graph foundation model is trying to solve that problem, basically asking how to make relation inductive. And in that way, we can basically say, okay, as long as we have structure of both relation type and also the node, we can learn over the structure pattern, and then they can generalize well. And that's like our goal, and that's our hope. And essentially, all the work right now is trying to design over how do we effectively learn over the relation type, which is unseen, and it can such that it can give like better results in the zero-shot inference time. So there has been a tremendous amount of work on KGFM, not really tremendous, because basically all the work I find, but please correct me if I missed anything. Essentially, there's been an increasing amount of work on knowledge graph foundation model in the past 2 or 3 years. And I guess the field is keep evolving, so I'm gonna share a bit of the thought myself at the end of the slides. Okay, so first, knowledge graph foundation model, what is it? So we are interested in a task called inductive link prediction on knowledge graph. So in knowledge graph, we only have a node and edges and relation type. Here, we do not have textual information, so the text is actually just for us. There's no node feature, there's no edge feature to begin with. So it's purely a structured learning base. So it's different than what Ben just introduced us about triple symmetry. In this case, well, there is no node features or no like node labels. Everything's pure structure based, and we cares about this link prediction, so which is like also a structure based kind of task. And the task here would be, for example, if we have a training graph which is about Bloomberg, Oxford, finance, HSBC, and about like finance kind of a finance knowledge graph, and let's say we only have that for training, and in testing side, we want to test on some completely different knowledge graph with completely different relations. And the only thing that is like sort of similar to each other is that their structure pattern are sort of the same. And a knowledge graph foundation model would be able to learn solely based on this pattern and transfer them like sort of perfectly in this sense to the testing graph where the relations are completely different. And yeah, that's a task setting. And in here, similar to this triple equivariance that Ben was introducing in the last tutorial, here we're cares about another type of equivariance, which is node and relation type. So essentially here, we want the model to learn there's a node correspondence between each other. For example, Oxford and Intel. And Oxford from the left and Intel from the right should be sort of in the similar position. Same apply for science and CPU. But in this case, well, if we just talk about node, and all the GNs can do that. But in particular, we also want to care about this relation type, which is we want to learn a mapping from provide to supply and research to produce, so that we can actually start, doing this link prediction on whether Intel has produced a semiconductor in the testing set without actually seeing Intel, semiconductors, or even all the relation inside. And essentially the idea here, well, we're just using a mean to reiterate. We try to find a way to generalize from the structure patterns instead of just memorizing the relation embedding. And the pioneers work, there's Ingram, there is Ultra. Basically what they're trying to do is they always find a way to compute this relation invariance, which is a structure property of a relation that is transferable across the graph. And a lot of people are trying to, well, a lot of the KGFM before are trying to do this pattern matching. And I'm gonna show you like how this is being done, like in the next slides. And essentially you define we call it motif, but essentially just like a small recurring subgraph pattern. For example, there's like a head to tail, tail to head, tail to tail, and head to head. It's essentially basically saying, for example, if there's a relation of alpha and beta connecting in this way, if there is such a relation, then we will have some like connections in our like layers. So this will be some information we need to care about. Okay. So let's start with the very basic. The Ultra is one of the first foundation model that being applied, and it shows really successful results, showing that they're actually better. The zero-shot inference of Ultra model are actually better than the end-to-end training of all the existing like traditional relational GNNs. And we start by a knowledge graph, which is Michael Jackson, right? Okay, Thriller, Disco, and Quincy Jones. And the question is going to ask, what's the genre of Michael Jackson? I guess, yeah. And to do this, let's say we cares about the motif, which is called tail to head. So by tail to head, it literally just means that we have a central node, there's a we go from we accepting a tail and we're going outward for a head. It's like alpha and beta here. So we view this as a little small knowledge graph. And to begin with, we're trying to map this alpha to some relation and beta to some relation as well. So let's say we find out, oh, actually there's a genre and author mapped compared inside that little example. So that must mean something, right? That means this genre and author, even though we've never seen it before, it has to share, like, I don't know, the tail of the tail of genre must share the same node type as the head of the author. Like, these are very implicit, but this is basically what it tells. So because this is valuable information, we store them into a relation graph. And we have a relation graph which is called author, genre, and collab. And we connect the edge between them. So we keep doing this for all kind of different motif as we have it here, and for all possible kind of way in the graph, so that it can actually generate a proper relation graph. And the idea here is that once you have a relation graph, you can do a GNS of a relation graph, which give you a relation embedding. And this relation embedding will change whenever you have like a different knowledge graph to begin with. And also a very interesting thing here is that because all the process here, because we're doing a relation graph instead of having embedding, storing an embedding, imagine if you have the similar thing with similar structure with completely different relation, then you would actually generate exactly the same relation graph. And that's how you generalize from different relation type. And well, by basically summarizing this kind of motif behavior and do this message passing over. Once you have the relation embedding, you just take any normal standard relational GNS, plug in the relation type, and get your results. All good here? Awesome. So this is one of the things that basically that the whole KGFM community are actually very hyped on. And the reason why is because if you check the light blue, the supervised SOTA method, you will see that actually you can have a single model that follows that equivariance, a relation, node and relation equivariance, and beats almost everyone. So it was not almost everyone, but like it has very competitive performances overall. So that's really give us a hope in the sense that we can actually have built one model and solve all the link prediction tasks here. Okay, so now that we have a working model, one would naturally want to ask, well, everyone GNs have like expressivity limits. Is this model we just present also have the expressivity limits? Well, the answer is, of course. And essentially, we come up with an example showing that, okay, if we just take the ultra that we just proposed, then there are some graphs that or triplets that you cannot really distinguish. For example, in this case, you have a very kind of like symmetrized graph. And the question is trying to ask whether there's a link from U to V1 and U to V2. And essentially, if you do ultra, well, technically, you only consider this binary motif, which is a 2-path, which is like always alpha, beta, that's it. You're not being able to distinguish between these graphs. And it's this very like, I don't know, how do I say, handcrafted counterexample, but this shows that there are some theoretical limitations over the model, and we then proceed to study like why and how. So just a spoiler alert, if we have a proof over that in the paper, but essentially the idea here is that the little flower inside, the R3, R2, R1, R2 flower inside, will create a full relation graph. And once you have a full relation graph, all the relation are, it's like clique, then all relation are like non-distinguishable to each other. Then you cannot distinguish between. So it's like very handcrafted. So, and we go back to the design of the initial graph foundation model, knowledge graph foundation model, like in Ultra, in all the others, like there's RMPI, there is Ingram, and we figure out they all cares about like binary relations. So there's alpha, there's beta, and that's it. And no one really say that you can only consider binary relations, right? Because there's always going to be like high order relation interactions. For example, whether a sequence of 3 paths, like alpha, beta, gamma is showing up, or whether there's like, I don't know, 4 different relations are forming the same kind of star. And no one says that you cannot do that. So basically we start by asking the questions, well, including these actually helps, and does it help theoretically speaking, or does it also help empirically speaking? So essentially, what in our previous ICML work, we basically show a general framework of KGFM. It's covered ultra. It's essentially a similar idea. You have a knowledge graph. You do this. You find the pattern. You find the motif you want to consider. For example, here we only cares about like alpha beta and alpha beta gamma in that form, P1 and P2 here. And then you, based on that, you construct this. You do this map, the same kind of like mapping homomorphism check. Create this relation graph as the same as ultra. But in this case, because now you care about like more higher order relation interaction, you have like hypergraph instead of just a graph. And then we do some message passing over relation to get a color. You see there's a blue, red, green, and yellow, I think, the yellow. And you map it back to the actual knowledge graph to any other relational GNNs which act as a entity encoder. And we essentially formalize this as an expressivity study, and we show that ultra is the same, has the same expressive power as essentially the motif, two paths, which is the one I just shown before. It's like the two like alpha beta in all different direction. And then we also theoretically show that actually there is a hierarchy. So if you choose this like small motif in a like smart way, which is proven, you can theoretically show it's more and more expressive, so you can distinguish more and more kind of different pairs of a triplet. But I think there is an upper bound about. So yeah, that's how we are trying to present the study of the expressivity. And empirically, we show that if we have the motif model, which is basically ultra, but not quite, you can start replacing the motif, and you see that as the number of the motif increase, the theoretical expressive power increase, and then the overall performances increase as well. And the same happens also in the fine tune. After you fine tune, you also have a bit of an improvement overall. And so we also like trying to get into this relation embedding and see, okay, let's plot the cosine similarity between all the relations and see how similar are they. And we do figure out that once you have a richer motif, the relations are more distinguished, so that it's easier for the downstream like encoders to distinguish between them and try to assign it different weights. Yeah. So no questions? Sounds good. Oh, I'm gonna do a question later on. So, and then we introduce something called stochastic KGFM, and it's quite. We basically start asking the question again. Well, all of the assumption of KGFM before was like, okay, we have no relation in covariance, which basically means that if there's a relation naming swapping, then the semantic should be exactly the same. And we started to question that. So here, for example, in this, I'm not sure how many of you know Star War. I'm gonna do Star War. Essentially here, we found a counterexample saying that, okay, if you swap this red and blue, which is like and dislike, the whole thing is still relational isomorphic to each other. And thereby, any of the knowledge graph foundation models should give the same results, same link prediction for all these two different green like arrow. But in reality, you don't really want that. I think like you don't really want Loop to be friends with Empire than the other like Han Solo. So essentially, we started to question whether the current KGFM have to abide this strict equivariance, or can we somehow relax them in a bit? So we do this by we propose another model, which is currently it's on our side. It's called Flock, and the idea here is very simple. So instead of doing deterministic message passing as all the GNNs are doing, we go back, we do this, go back in time, using, I don't know, 2013, 2014, where the random walk is very popular at that point. Random walk on graph is learning. So essentially the idea is very simple. We have we start sampling random walk, and to make it a foundation model, we cannot really store exact relation ID. So we have to anonymize them by basically the way the whole idea is trying to make the relation map the relation back into shared embedding table, so that this can actually be like transferred into the new relation graph. So we do this recording protocol, which we start to like note down what's different random walk. Like one would be like this is the first node I've seen, and if there's like a repetition, for example, alpha and alpha, which is a relation type, then we notice that they're the same relation type. So we do this, and we put them into a sequence processor. For example, some GRU, some transformer. You can be LLM, but for now, we keep it simple and put it into a GRU. And after that, we try to do something called consensus protocol. It's basically just a pooling layer, trying to map it back to the original graph, so that each relation will have the same embedding after one iteration. And the whole idea here is like this version of KGFM learning on the random walk instead of message passing will compute something called probabilistic node relation equivariance, and it's actually quite good. So the goodness here is that because it's probabilistic covariance, in expectation, there are still relation equivariance. There's still like relation equivariance coming up, and which really guarantees us a lot of like performance boost. So the performance are still like sort of maintained. They're even surpassed the previous version. But also due to this random walk, we actually can achieve this universal approximators over isomorphism invariance link level function over knowledge graph. And as a result, because they are sort of like already breaking the invariancing a bit, we can't be able to distinguish between like and dislike. So it was actually pretty cool. And we show that we're like much better in terms of both entity prediction compared to like Ultra and Trix, which is another foundation model I'm going to quickly explain. And we can also do relation prediction. And the good thing here, also another good thing here is that because in random walk we actually record a relation and entity at the same time. So we don't need to go through this two-stage process. Like we don't need to start with relation convolution and then go to the entity convolution. Here we just do one time of sampling and that's it. So it was actually pretty elegant. And yeah, so these are like three different work I was trying to introduce. I'm gonna quickly introduce some other just to show that the whole idea is pretty much the same across all of the different everyone in the fields. They share the same idea essentially. And there's one work recently, it's called SEMA. So people are gonna ask, like, we always have this structure. Everything was based on structure structure encoding, structure learning. But in reality, the KG come with a text. So how can we utilize this text? Well, there's a paper recently called SEMA that got accepted into, I think, EMLP 2025. And essentially we're saying that, okay, instead of having this relation convolution as the top part, which is structure part, we can additionally concat versions of relation, like texture information, some by LLM. And the similar thing would apply to basically everything I just said before. All the KGFM there, you can sort of following the same paradigm, use some LLM, use some other like language model to get the embedding and try to concat them. And this will give you a sort of like more informative feature in that sense. So another thing I want to talk about is another KG foundation model called Trix, and the idea is also quite simple. So instead of only have relation convolution and then encoding node convolutions, you can do this iteratively, so that relation embedding will be more refined that way. And also in this way, you can allow to direct relation prediction. So it's actually pretty cool. Like all of the work you can see like basically all of the work are following like Ultra to begin with. You always have like some kind of relation graph you want to build based on a motif, and then you somehow do message passing over the relation graph so that you can get a relation embedding. And this relation embedding is transferable across like different. Well, it's not transferable. It's sort of like an in-context learning in some way, so that in the test graph you don't need to update the weights, so that you can compute the embedding and do your message passing or like something else. So that's the whole idea of knowledge graph foundation model. And one would naturally gonna ask, well, now that you're on the third stage knowledge graph, how can you even apply the same idea into the hypergraph? And this is what we do. Well, just for those who don't know, knowledge hypergraph would be a strict extension of knowledge graph, where you, instead of having two entities in each edge, you have a hyperedge, and this hyperedge is ordered. It has a relation type, and it can take multiple entities there. It can take, for example, there's a at conference will be like 5 entities, and at fair will be also at 5 entities. And this will basically, and this idea, similar idea actually follows. So if you think about it, all you need to do is trying to summarize like this motif type or interaction type. And here, we just need to create a relation graph as always, have this grail. We try to come up with those edges. For example, here, we can say, okay, an edge from R1, R2 will be assigned to something like, for example, 3, 2. And the question, that would mean the third position of R1 and the second position of R2 has to intersect. Thus, they must share the same node types, and thus, this relation, even though we never seen it before, has to have some connection between. And the similar idea apply, you get a relation graph, you try to encode your relation graph using message passing, and then you get your relation type, and then you put back into the standard GNN. So everything it's like everything is a huge loop, and we go back to the origin, yes. And I'm gonna briefly discuss what I think will go next. Of course, there's a lot of interest on KGFM. There's a lot of interest on relational databases, and I think the whole KGFM are actually suited pretty well with the relation database. So there's one possible direction that we are thinking of. And also, of course, all of the current KGFM model are trained and tested on these academic data sets, which is quite small. And the one way we're trying to make it work is try to see, okay, whether there's a good scaling behavior, which I don't think, given the current data set, I don't think there is much of the like the hype on the scaling, but there is still some scaling behavior happening. So we are quite interested in how this can be done to billion size of parameter. And finally, there's always going to be talk about, for example, can we just treat LLM as a KGFM? Can we just use LLM instead? There's a different way to input LLM, which Zifeng's going to talk about it next. For example, you can sequentialize the input and just use that instead. Or you can have some tool just to try to call this external databases or external knowledge graph to try to get some sensible information. Or finally, you can even take a GNs, get a graph tokenizer, and get a, yeah, I'm not gonna talk about it so much, but Zifeng's gonna do that. And finally, we're also thinking about how do we, well, there's another kind of foundation model, which is tabular foundation models, and we're thinking how this KG structure could be encoded. It's a bit different there because in the standard knowledge graph, you don't have no feature, and we have to come up with, like, there's no really like aggregation coming in, so we have this kind of idea of how to sort of make it work, and yeah, it's still ongoing, so. Essentially that's it. I think I'm running a bit fast, so I guess I'll give some time for the tutorial to be set up. So if you go back to check the same GitHub pages, there will be a tutorial part 2, and then I'm going to explain how you can set up the KGFM and how to run link prediction for zero shot. Yes. Just wait for like 3 to 5 minutes.
While we are waiting for the setup, please also feel free to ask questions for the audience here and also for the audience online. I will be monitoring them if there is any.
give it another minute. We start at precisely 5. Okay. So essentially in this collab, I'm trying to implement one of the first graph foundation model, knowledge graph foundation model, which is Ultra. And essentially, yeah, we just go one by one. Essentially, we have this task. We start with task setup, talking about what is the index building prediction and what is the example. How do we do this known within the relation permutations? And then we are going to the more technical part, which is how do we build the knowledge graph foundation model. And we essentially talk about how, particularly how Ultra is being built and how they are using these 4 different kind of motif of like binary motif. And how do we do this pattern matchings to get the corresponding results? And how do we build a graph, relation graph? We do message passing on the relation graph, and we do message passing on the final like entity graph. And finally, we are gonna define it and load the model with a predefined check with my pre-trained checkpoints, which I've trained, and I'm gonna basically demonstrate how this can be carried out as a zero-shot inference. So the model will not be trained, well, the model will not be trained on the same data sets, and it will perform pretty well on the other data sets that is like completely different. So yeah, let's get started. Okay, so essentially, yeah, I'm basically repeating myself. We're trying to do a link prediction on knowledge graph, and this time it's inductive on both node and relation. So what that means is that in the testing time or the inference time, the relations will be different, and the nodes will also likely to be different. And the idea here is trying to figure out what is being preserved, what's the invariance over it, and how do we learn over this relation invariance. So we do a bit of a setup. So knowledge graph is a directed and content typed relation, which is a bit different than the traditional graph. And all we want to do is trying to compute relation invariance, which means a function over the relation in the graph such that if you try to permute the relation or even change the relation completely, as long as the structures are intact, the model should return the same results. And the way we do this is, again, more particularly by constructing this relation graph. And non-particularly, we're trying to, like more generally, we're trying to capture this transferable relational patterns. And this is the only way like we can try to expect any generalization to happen. And yeah, so this is go back to the example that we had before. We have HSBC, Finance, Bloomberg, Oxford, and the idea here is that like this is the same PowerPoint idea we're probably gonna skip. The idea is here trying to predict Intel produced semiconductor, given the fact that Oxford had research on finance. And the reason why we can do that is because we have a very similar structure on the both relation type and the node type. So yeah, so the whole section 1 is basically just explaining. It will be pretty much similar to what I had in the PowerPoint. So yeah, in the next step, we're going to talk about knowledge graph foundation model. And yeah, I'm probably going to skip running this because it's probably, I guess I can just run this. I'll skip it anyway. So we have, we installed Torch Geometric. Then we start defining this model architecture, which is Ultra. Yes, okay. And in Ultra, we have 4 different types. We have tail-to-head, head-to-tail, tail-to-head, head-to-head, and tail-to-tail. It's essentially the alpha and beta, like 2 different kind of relations combining a different way. So head, tail, tail, head. And the pattern matching is the same. If in your knowledge graph, if you have any 2 relations that satisfy any of this pattern, you will try to connect the edges from these 2 relations in the graph. Okay. And then you're gonna apply relation encoder, but I think the order is a bit, yeah. So we go down here. So if you try to run this, it will download the corresponding checkpoints that give you the already trained version. And it's called 3G reproduce because I basically trained myself. It's not the one on the official Ultra website, but essentially it's being trained on the same data pre-train mix. And yeah, so basically you want to download this, and you start by building a relation graph. And so technicality-wise, I can show the code here. How do I show the code? This, yes. So technicality-wise, how do you actually compute this agency matrix, which is on the relation graph? So this head, hand, tail, tail, head, tail, tail, head. There's a very neat trick we are using, which is called sparse matrix multiplication. And the idea here is that you can start by constructing this features called EH and ET, and essentially telling what is the edge type over what's the inputting and forwarding edge type in the original knowledge graph. So you will come up with a tensor, a matrix, which is relation types times number of edges, number of node. And then the whole idea is that if you want to get a relation times relation, you just multiply this EH matrix and ET matrix in all kind of different possible ways, which is 4-way actually, so that you can get the connection. So whether two relation has been mapped in this way. And technically, when you do that, you also compute the number of the relations, so you actually get the relation count instead of the existence. And in Ultra, the design here is that we are trying to skip this count and only take up the relation. There's also some work studying whether including this count could actually make the model more powerful. And theoretically speaking, yes, because now that you can distinguish more graph that, for example, there's some multiple duplicates over the similar motif. But however, in reality, we figured out that without the count, just keeping the existence of 1 or 0 would be more beneficial. So we run this, we run ET and ET transpose, and we come up with a sparse matrix multiplication by computing this EHT, EH, ET, ET, and all these. And this works for binary path. This works for even ternary paths, where you have 3 and even 4, you can do infinite amount. But in reality is that once you start doing this ternary, there's already a lot of problem with the memory and engineering problem just starting to kick in. So there's a recent work that basically there's some recent ideas on how to make this work for the arbitrary types of motif. And the way we're doing this is by encoding the motif using some SQL or some database languages, and try to use that because database is quite heavily optimized in the past decades or even more than decades. This will give you a count to begin with. And also, technicality-wise, we should build this relation graph every time because every time we want to do a training over some link, we have to mask out that link, which this behavior might actually change the relation graph. So we constructed this edges, this agency matrix, and then get all the edges, and then we create this relation graph here, where the edge index will be just all the different kind of index in this 4 relation concat together. The edge type will be the corresponding type, and then we'll be having a 4 relation because there are only 4 motifs. So in the relation graph, it will also going to be a knowledge graph as well. So there will be 2 knowledge graphs happening. Then once we build this graph, all we want to do is trying to reason over it. And the way we're doing is actually quite standard. 2 message passing, 1 on both relation graph and 1 on entity graph. In this case, we all use a model called MDFnet. And the idea here is we do this conditional message passing where every time you fix a query inside your graph, so for each query compute a different relation, a different hidden dimension, hidden representation. And then in the relation encoder, well, these two are pretty much the same, except in the relation encoder, your input is you're operating on the relation graph. So the relation embedding will be like aggregated and transformed, aggregated and transformed. And once you compute the relation embedding, you plug it back to the entity encoder where it's another MBFnet. But this time, because well, one cannot really expect the relation encoder and entity encoder to have the same size. You need to have some MLP, some projections to map it back to the same size. And this way, essentially, these are like a slight modification. You're basically running two MBFnet at the same time, and sequentially, so that you first get a relation embedding model representation, and then you get the entity representation, in which you can use them as a decoder. So we have a generalized relational convolution network. We need to define this project relation. It depends on whether they are in the relation encoder or the entity encoder. And then in the forward pass, we just try to do a message passing, and aggregates. In message, we use multiplication. So we have a relation embedding, and we will just multiply the input, and that will be our message for each edge. And then in aggregation, in here, we just use summation, which is the simplest and the easiest to do, yeah. So yeah, and then we define basically two MBFnet. One's on relation MBFnet, which we have this, we just do Bellman-Ford. Like Bellman-Ford is essentially, we have a special way of initialization to just to indicate how the query is. And then we do standard message passing over. And the same apply to the entity encoder, but in this case, because we cannot really initialize the relation embedding to begin with, we need to take the relation embedding computed from the previous step, which is the relation encoder step, plug it back to some map in MLP, and then throw it back. So here, the multiplication will be on MLP over the relation embedding. And in entity encoder is pretty much the same. I'm probably gonna skip here a little bit. And there's a neat trick that I found it very, very useful to make everything generalizable. And here would be essentially during the training, you have to remove. So let's say you want to ask a question like whether there's a relation between A and B. If you're training over that in this MBFnet style, there's one thing you have to do. You have to remove this A and B inside. Otherwise, it's gonna quickly get overfitted and everything just not gonna work. As opposed to traditional message passing, where when you try to do like prediction between like two different nodes, you don't have to remove anything. So this is some tricks that really help the model to generalize. And because removing that will cause the whole relation graph to change, it might cause the relation graph to change. We might to make it very rigorous, we need to rebuild the relation graph every time you do this training, which might take a lot of time. And essentially, the general framework will be the same. We use the same message passing neural network. Technically, you don't have to throw in the MBFnet. It can be anything. So in Ingram, which is a previous work from Ultra, they use, I think, GAT version 2, a relational version of GAT v2, to be both relation encoder and entity encoder. Please correct me if I'm wrong. But and essentially, we use this also in the motif paper, and the reason why is, well, there's some like neat tricks in the theoretical part where if you just take summation and you do aggregation, linear aggregation over summation, you can sort of show that they're injective, and it's yeah. And once you implement the Ultra model, you see like it's very simple. You have a relation model, you have an entity model, and every time you start by having the query, you compute the relation representation from the relation model, plug it into entity model, get a score, and return that score. And this score will be either like from 0 to 1. It's a binary classification asking whether this link would exist or not. Yep, and I think we're really good on time. So part 3 will be running the model. The data set will be well, it's like very nasty code. I'm not going to show this. Essentially, we're going to load data sets, and we're going to load different kind of data sets to try to directly inference over. But first, we're going to talk about a bit of a difference, like how do we measure like metrics in the link prediction task. So in the link prediction task, we always sort of do this ranking metric, and they are essentially min rank, min reciprocal rank, which is MRR, and hit k. I assume sort of like most people know how the link prediction work, but in case not, so min rank would be essentially in every query where you already know the relation type and you already know the source node, you want to ask the target node. And the way you do this is you try to ask this question on the graph using a GNN, and you compute a score for every other possible candidates after filtering, of course, or you can be before. And then you find out the ranking of your correct target as opposed to all the different target. And that will be the rank I here, and MR would be if you do that multiple times and try to find a mean. And MRR would be the opposite of that. So MR is the lower the better. MRR will be higher the better. Hit will be something similar, but in hit you only cares about whether the correct answer is being mapped into top k. So normally we use case hits at 1, 3, and 10. So 1 would be whether the model could correctly identify like the correct target is actually very high. And the 3 and 10 will be like similar, like whether they're in top 3 and whether they're in top 10. So we proceed by defining the experiments. So there's because we are testing a different knowledge graph, there's a different setup, so we need to load them in different ways. Sometimes the validation has some problem, like technically the validation should be, in the purely inductive cases, the validation should be sort of similar to the test, but some traditional work, like some literature are showing that this kind of work, they have the validation actually on the training set, so we need to take care of that in this part. So we have this testing over here, and running the model is essentially we generate all the negative. We use prediction. We run the forward pass on the model on this test data, which is the graph, and then all the batches that are like tail and all the batches that are head. And in this case, the size of the T batch will be all possible entities in the graph. And then we compute the metric, and we'll get the results. So and in the experiment here, we have this pre-trained checkpoint, which we had, called 3G reproduced, and it was pre-trained on FP15K, WordNet, and Codex Medium. It's the same as how Ultra is being used. And then the model never seen anything in NAIL datasets and in Wikidata. So it's like these are like completely different kind of knowledge graph. And our hope here is trying to see whether our pre-trained model actually generates sensible prediction results in NAIL and Wikidata, like on Sing knowledge graph. So we can go ahead and click the run. It should be really quick. If we do that, then we have a bunch of results on the testing data sets, MRR, hit 1, 3, 10. And there will be a check. So technically, you can go ahead and check whether this is actually corresponding to the correct one. And spoiler alert, it is. So feel free to give a check. So part 4, I'm not going to have any code here, but I'm just briefly introduce how a different paradigm, like the random walk session, which is called Flock, is working. And it's more like some kind of discussion. So we've talked about this in the previous slides. And that's pretty much it. So I'm way ahead of time. But yeah, any question, I guess? Okay.
I'm sorry if you already covered this, but it's not clear to me, like, if you, at the end, you get a mapping between relations across data sets. For instance, if I give you like So if you actually give a mapping, whether you can constrain on that mapping, for instance, to make sure that the types of relationships follow the same count or any other constraint that could be relevant.
So we don't explicitly construct what kind of mapping is being produced, but these sort of like basically you're okay. Let me just try to get the question correct. So you're saying whether there's explicit mapping across relation type.
Yeah, for instance, like say if I train on like a protein network and then I apply this to like maybe social data, then maybe you find that this relationship in proteins actually is being mapped to this relationship between humans, like whether you can interpret if your model is doing what it's supposed to do based on that.
I see. Okay, so there is no explicit mapping providing because the whole of these like relation, we're all mapped them into the same relation graphs, and essentially the similarity would appear when you figure out whether these two relation graphs are sort of similar to each other. So for example, if you have a protein, there's like, I don't know, double bonds, and you have a citation network, which is like cited. If you, there is no specific like mapping, like the model will not tell you whether this relation will be exactly mapped to the other relation, but you can tell by seeing that if the corresponding relation graph, once you generate it based on all these motifs we talk about, whether these two graphs are similar to each other, and if so, which two nodes are similar to which node in the other graph. And this way you can sort of like have some kind of a indication on how these two can be related, because at the end of the day, the relation embedding will be the same if the graphs are the same.
And have you looked if the relationship makes sense, like for some examples?
So we have looked into this, but unfortunately we didn't have the example here. Essentially, we're mostly looking for it because we cares more about whether two relation, even though they're different, has been mapping this like very similar kind of situation where the upcoming model cannot distinguish them. And there is some, especially on some data sets where the structure are very much like close to each other. And essentially that's the reason why we start the whole idea of why do we actually care about the relation equivariance? Can we make it stochastic in a way?
Thank you.
So is there any more questions? Okay, so we're gonna take 5 minutes break again, and we're gonna introduce Zifeng to talk about LLM as graph foundation model.
Hi, can you hear me?
Hello? Can you hear me? Someone, can you hear me? Hello? Hello? Yeah, he cannot hear us. He said he cannot hear us. But I guess it's fine. Hello, hello. The test here? He can't hear us. Yeah, he said he cannot hear us. I guess it's fine. But... We're 2 minutes in. Starting.
Can you hear me, Zolf? Oh. Yes. You're good, you're good.
Okay, so whenever there's a need for him to hear the comments.
Yeah, that one.
Otherwise, we just leave it.
Good. Yep, so please. Okay, let's do it. So wait a moment. Okay. So next part, I'm going to share with you everyone about large language models as graph foundation models. Um, so first, we all acknowledge that there is a heated topic. Let's say, can we train a model to reason any graph? That's why we are having this tutorial right now. And preliminary works may be covered by Xingyue and Ben. They are about graph foundation model based on the graph neural networks. So as I switch my direction a little bit to natural language processing, right now I deal with a lot of large language model stuff. So I try to see if I look back, if I'm trying to solve the same graph problems, can I approach it with the language models? So this conversation is actually artificial, but it's more or less the same when I'm talking with Xingyue offline. So I was asking him, why can't we use language models? And he said, no, graph foundation model should have some characteristics, la la la. And actually, I'm not a theoretical person. So I actually don't care about it. So I said, as long as they work in the real world scenarios, and these so-called large language models are very powerful in text generation, and we can leverage it. And we can transform the graph problems into text generation. And if we achieve that, we are good, right? And after that, let's first take a look at what might be the advantages of building GFMs using LLMs. First, we all know that LLMs are very huge, and it's even getting larger and larger through the years, right? And they are very, very powerful and big parametric functions. They have a lot of parameters which can absorb the knowledge when they are doing the pre-training. And language models, they are inherently explainable because they are generating the text while doing the decision making. And language models can help to unify all graph-related tasks with next token prediction. And here, I'm writing next token prediction here is because for me, the more I deal with language models, I feel that scaling law is not the most important. The most important stuff is the next token prediction because it literally unifies everything, unifies every task. And if we take a look at previous works about graph foundation models using GNNs, a lot of works they tried to do some node classification or something. They are only trained on this task. They cannot generalize to any other task, but the language model can naturally achieve that. And okay, then after we see the advantages, let's see how the pioneer works, or let's say the preliminary works, they are trying to use language models to achieve something like graph foundation model. The first type of works, they are using a prompt-only method. So this is more or less the first work by Wang, these people, published in 2023 already. And they try to formulate all graph-related problems into unified question answering form. And this kind of question answering form is still adopted currently in all kinds of works that combines large language models and graph-related problems. And then you can freely define all kinds of graph-related problems and just try to ask language model, how can you solve it? Can you solve it for me? And large language models will generate some text telling you the answer. And then in this work, they are using the different prompting techniques. Now, maybe we look at these techniques, we feel that it's so easy, but at that time, it's quite novel. So people were using chain of thought, people were using in-context learning. If you're familiar with this stuff, you might know that actually COT and ICL are very, very common techniques used in all kinds of large language model reasoning scenarios. It is not only constrained to graph-related problems. And also for these authors, they propose another technique called the build a graph and algorithmic prompting. If we take a look at the prompts here, in the middle, it's a build a graph prompt. So first we will have some example. This example is using some text to describe some graph. Just like the node 0, node 1, there's an edge connecting this one and that one. And this build a graph prompting first will let language model to build a graph on its own. So even if we don't know how the language model will build a graph, but we actually give in the language model cue that, okay, you need to build a graph first, and you're dealing with some structural data. And then the language model might be aware of that and try to improve its performance. And for the right part of this slide, we can see this algorithmic prompting. So if we are writing code in the Python, we have some kind of like network X packages, right? And these packages will have some classical graph reasoning algorithms. And these algorithms are there for solving some graph-related problems. So in the algorithmic prompting, these people just trying to tell the language model, okay, now you can use this algorithm, just do it. And then the language model might understand it and use this algorithm to solve the problem, right? And after that, people try to approach it in another way. So these Fatemi, these people from Google, they're trying to focus on another part in the prompt. So they try to decompose the prompt into two parts. First is the encoded graph. Second is the instruction, and as well as the question. So the previous work is dealing with something about the instruction and question. But in this work, they try to play around how can we encode the graph. So how can we encode the graph? They call it the graph encoding strategy. If we take a look at the picture here, we can see that for the same graph, for this graph G, we can use a diverse set of expressions. For example, we can formulate it into a social network. We can formulate it into co-authorship or friendship. Actually, by formulating them into different kinds of ways, it is just giving the language models different context because we're telling them to understand in a different way. So this is what they call the graph encoding strategy. They found that actually you change a formulation of a graph and then the performance will be affected, sometimes with a great margin. So this is also some very interesting finding. And after we have seen these works, people start to realize that, okay, then the language models, even if they are not optimal in solving graph-related tasks, but they still have some potential, or let's say they're still showing some performance that is reasonable, and they are willing to solve these problems. So then people start to think, okay, maybe we can tune the language model to achieve that. How can we do that? A very nice work that I'm still looking into nowadays is the graph token. So graph token is that it uses some graph encoders, such as we are very familiar with GNNs or graph transformers. They try to treat the representations of the nodes as the soft prompt. So what is the soft prompt? Soft prompt is something like, for example, when you're using a language model, you're trying to encode the text into some tokens, right? And a soft prompt is that some tokens that is prepended before your text tokens. And these soft prompts can be tuned when the language model is trying to tune itself. And then by only tuning these soft prompts, these low-dimensional embeddings, we can achieve how to adapt our language model's ability to different kinds of downstream domains. This is what the graph token was doing. So here, these green blocks actually means the node embeddings, or the average of some node embeddings. Anyway, it's graph-related embeddings. And the LLM, it says that here the LLM is frozen, but actually if we are thinking it in a soft prompt way, actually the LLM is not completely frozen. Like even if there's no parameters here tuned, but the parameters here related to the input graph tokens will be tuned. And the loss will be backpropagated to the GNN and graph transformers. And this is how they do it to achieve the domain adaptation. And we actually observed that graph token significantly outperforms previous methods. It is a very great improvement. And there is a concurrent work called GraphLLM. It is actually similar to graph token by using soft prompt tuning. And here they have an additional module called textual encoded decoder. It enables them to encode the textual features in the graph, and then they try to put them together with the graph transformer that tries to learn the structural information of the graph. And then they also compress this information into some marked as red, these low-dimensional embeddings, and only tune on these embeddings. Of course, there are the third work. There is a third work, and the third work is also kind of similar, even if they are having some little difference in the technical implementations. So this is Laga, also one of the work I really like here. It is using the graph encoder same. Now he's using the graph transformer and an MLP projector to adapt the graph information. And the difference is that Laga is using an MLP projector rather than directly tuning this soft prompt. And all of the parameters that are tunable in Laga is only this projector, which is quite small and which is quite efficient. And by encoding the graph, Laga tries to encode some kind of like graph Laplacian and also the hopwise information. And we can see that these works are more or less similar, right? And after that, in this year, I think everyone knows DeepSeek right now, right? Even if you are not very familiar with reinforcement learning in large language models, you definitely know DeepSeek. What it is doing is that they are trying to use reinforcement learning to let language model self-explore how to solve some problems. And if the language model happens to solve the problem in a very good way, it will get a high reward. If it cannot, it will get a low reward. And in this way, it lets language models to gain some reasoning capabilities in different kinds of domains. The most heated topics are around how to let language model enhance the mathematical reasoning and coding. But in graph, we can also do that. Because when we want to solve graph-related problems, we always have a phrase called graph reasoning, right? We have graph reasoning. So graph reasoning is a reasoning problem that can be enhanced by using the reinforcement learning, okay? So RL can be used to incentivize the capabilities, and it also promotes explainable graph reasoning. And explainable graph reasoning is really, really important in the real-world deployment. I will talk about it later. And also, SFT requires human-curated reasoning traces for LMs to learn from, and these are all previous work we're doing, while the reinforcement learning lets LMs to discover these traces by themselves, which helps them to generalize. And a very, very notable work, recently, I really like it, is called G1. The G1 is basically, in short sentence, it is just that using the reinforcement learning to train a language model and then try to introduce some capabilities in solving some graph theoretic reasoning problems. So in G1, it also proposed a very large-scale dataset called ELDOS. I don't know how to read it, but I hope it's correct. So it is constructed by containing diverse graph theoretic reasoning tasks. They have 100K training data and they have 5K tests. And here is a table of all of the tasks and the ratio and the performance of G1 and ELDOS. And you can see that they even have a split into easy, medium, hard, challenging, which is difficulty level, as well as considering a very, very diverse set of tasks. How G1 is trained, and since it's a tutorial, I'm trying to give you more details here because I know that most of you guys are not very familiar with LLM post-training. So what is LLM post-training is that when we train a language model, the first step is to do pre-training. It is just like let them memorize everything in the world. And then after that, we want language models to be helpful with people, to be not showing some toxic content, to be very friendly, to enhance some part of like downstream tasks abilities. All of these stuff can be forming the stage called the post-training. So post-training will normally be split into two parts. First is the supervised fine-tuning, and second is the reinforcement learning. And why we do the supervised fine-tuning in the LLM post-training is that we try to fix the format of LLM when it is trying to answer some questions. When you use ChatGPT, it says, I'm happy to help. These are all like fixed by supervised fine-tuning. And also if you use the prompt, if you use the API to call the GPT or Claude models, they will have user assistance, these kind of special tokens, right? These kind of special tokens are also trained during the SFT phase. So SFT phase is that we need to have very high quality curated data to let it follow instruction to make sure that they will not say something which is undesired. So in G1, what they do in SFT is that they try to have some very high quality chain of thought to make sure that the answering of this model will follow this type of format by answering some chain of thought in a very helpful way. And how this chain of thought data was sampled, they're sampled from the answer of the Qwen 2.5 32 billion model. And you can see that their COT collecting model is 32 billion and the trained model is 3 billion because they want to keep as much higher quality as possible ones. And they also only keep the only corrected instances when they try to collect the SFT data. And after that, after we have SFT, let's say G1 already knows how to speak in the proper way, and they use the reinforcement learning after this SFT model by using the GRPO, which is very, very common algorithm in doing IL fine-tuning. And we can see that from observing the right side of this table, we see that G1 actually is really outperforming its base models as well as some other baselines, proving that IL helps LLM generalize well and acquire reasoning power on the graphs. Okay, so after that, we see that G1 is already doing a very good job, right? Can we turn LLMs into temporal GFM through fine-tuning? Why I want to have this one step further is that, okay, the most straightforward reason is that I'm doing temporal graphs. I was trying to think of this problem even before G1 was out. And then I saw G1, I acknowledged that it is a very good work. So by knowing that G1 is there, we still haven't solved the problem is that how can we deal with the temporal graph? Because temporal graph is different from static graph because it includes not only the graph reasoning, but also the temporal reasoning. And also in temporal graph, there are some very tricky use cases, for example, forecasting. So reasoning over temporal graphs requires temporal reasoning, and reasoning over temporal graphs usually need to deal with future forecasting, right? And future forecasting is very tricky. I will talk about it later. Well, the explainability is much, much more important. But if we think about using language models, we still can leverage the advantage of language models that I mentioned before. It is the explainability, right? When we try to generate some tokens, when the language model is telling you something in the text, it is what we call in language model, it is called the test time scaling. And there will be some increased inference time, and it will lead to higher accuracy, empirical finding, higher accuracy. And then, of course, it will naturally generate extra tokens. And these extra tokens can help us to get greater explainability, which might be very useful in some use cases. And this explainability is directly tied to the trustworthiness of a model. Because if we see the explanation of a model is okay, we think it is reasonable, we are more willing to trust this model. We are more willing to put it in the real world use cases. If it is not, we will never deploy it, right? And when we come back to the problem that I have mentioned about forecasting, we see that actually explainability is very highly desirable in this scenario because it is often applied in risk-sensitive contexts. If you guys are very familiar or maybe familiar with the temporal knowledge graphs, you will see that, okay, a lot of temporal knowledge graphs are about the political issues, and it is actually used in some government to help the early warning systems, to build the early warning systems. So in a lot of forecasting scenarios, there are risk-sensitive contexts. So it is very important for us to know how can we trust these models, right? And we typically have no ground truth labels before the actual event happens, which means that in the real-world deployment, we will never have the labels. And how can we deploy these models are totally decided by whether they can be trusted or not, and whether they are explainable or not. And that's why I think that the labels, the ground truth labels in these forecasting datasets do not mean everything we want, and we need explanations to indirectly evaluate the quality of our forecast. Okay, then it leads to this work. It is a very latest work of me, also Xinyu and Andy from yesterday. So I will spend more time on talking about this work and to see whether I can tell you guys how can we train with reinforcement learning to achieve graph reasoning. So in this work, we try to let LLM explore how to better do reasoning in order to achieve more trustworthy and more accurate forecast at the same time over temporal graph links. And here we will use some historical information from the historical graph context. Let's say it's the historical temporal neighborhood. And an LM will do some trial and error I mentioned before during the IL, and it will experience how can they achieve the higher rewards and how will they not be able to achieve the higher rewards, and then try to gain some signals out of it and do the reinforcement learning. That's why we call it the self-exploring language models, because it is doing the trial and error by itself. And we did the first modification is that in the temporal graph link prediction, previous works are trying to formulate it into a binary classification task. It is just that if we have a query, if we have a link UQ, VQ, and TQ, these people will ask whether it will exist or not. But when we do the language model, since we're doing the generation, we don't have to do this for all of the links, right? We can just try to generate in one query. It is just we ask, if we have a query UQ and TQ, can you tell me what is or what are the nodes that will be existing in this question mark? Okay, so we're just trying to formulate it in this way. It will help us to achieve very great efficiency. I'm not going into details here because I know not a lot of people, not everyone is interested in this part, but it will just remember it will help us to increase the efficiency a lot. And after that, let's take a look at how our method looks like. So this is how our method looks like. So let's get back to the formulation. Now we have a query, UQ, TQ, and we need to know what is this question mark, right? And we have its history. The history is that every graph edges that happen before the question timestamp, TQ, let's say query timestamp TQ. So we use this HTQ to represent it. And we will first use some kind of module called temporal context graph selection module called TCGS. It will help us to construct a context graph. We use this GC to represent it. And we think that it is most relevant to the query based on our histories. This is some deterministic algorithm here. We don't do any learning here. And we try to verbalize all the links in the GC. What is verbalized? It's just that we just try to say, okay, if we have some edges in GC, we try to list out the triplet, the source node, destination node, and the timestamp, just in text, no other tricks, just in text. And we try to combine them with the natural language question derived from the query, right? We just want to know about the query here, so we will use a natural language question to ask, okay, what is question mark here? But in a more concrete form, you will see later. Based on our template, capital Q, yeah. And we will feed our questions into the language model and try to extract the prediction answer after language model tell us a lot of stuff as the output. And we try to compute a link forecasting reward for each prediction, because in link forecasting, we might know, we might need to have some function to tell us whether it is doing a good forecasting or not, right? Okay, so first let's see what is TCGS. TCGS is that we input the graph context as text, as I said, into the language model. This is also a little bit tricky here because, of course, we can use some kind of like black box ways to encode the graph into GNNs with GNNs or graph transformers. But in this ways, the language model will see some low-dimensional embedding rather than the text, and it was not trained to understand these low-dimensional embeddings, and it cannot output anything that is useful in output, which means that our RL training step will be completely a failure. So that's why in this work, we don't try to solve this problem. We just try in the most naive way and to input this kind of text into the language model. And we aim to include as much relevant graph information as possible. That's why this TCGS is just based on some kind of like personal page rank in a temporal way. Okay. So I don't want to go into a lot of details here because these equations are based on very, very apparent heuristics. It means that, so to give you a very short introduction or a very high-level idea is that we just try to make sure that when we sample the historical graph, we want to sample the stuff that is temporally closer to the query's timestamp and that is closer in the hop-wise to the query node, UQ and TQ. That's it. That is very easy. And we don't need to understand what this is exactly about. It's just like some softmax function trying to tweak around the distribution. And after that, yeah, I put this in a very detailed way, but let's just go through this example to see how it works. We have the UQTQ. It is a temporal node here. It's not only representing the UQ node, it's also representing the state where UQ is at the timestamp TQ. And then for UQTQ, it has two one-hop neighbors. One is E1T1 and two is E2T2. And the two-hop neighbor is E3T3, right? And also, E2T2 not only will serve as the one-hop neighbor, but also will serve as the three-hop neighbor. Because if we follow this edge, it will be like 1, 2, 3, go to E2T2. And also, if we go from the right side, we just need to go for one hop. And that's why the score of E2T2 will be the sum of going from a three hop and going from a one hop. So in the end, we will compute some scores for each temporal node in the historical neighbor. And then we try to do the ranking and try to take the ones which are having the highest score. This is what TCGS is doing. And after taking this, we try to extract these important temporal nodes and try to extract the relevant, the related edges that was in the past history. That's it. And after that, we have this, I'm going to show you this prompt. Like I have said before, this is exactly the prompt that we are doing. And the question is here, could you list all plausible query destination node for the query source node UQ at the query timestamp, right? It is just a QA formulation. It directly asks you to return all of the nodes that might be the answer here. And here, the green part is the links in GC. It is that we take the TCGS and we take the context graph. We try to like textualize everything in the form of triplets, right? And these are the instruction here. These are very, very important because it helps us to regularize, or let's say standardize, how can we extract our answers and do the correct evaluation. So first, I will tell them, okay, you now need to do reasoning. So in reasoning, in the field of language models, we have this thinking tags. It is a very common way to do that. I'm trying to let the model to put all of its thinking into these thinking tags. And then I try to tell them to put all of the answers, like without any interference of thinking, into these answer tags. And when I do the evaluation, I can just extract from this answer tags, and then I can just do the string matching or whatever afterwards, right? And as I said, the last part I have mentioned maybe 2 or 3 times before. If the answer contains multiple answers, please provide all of them. In this way, we just do one query for one time, and it already covers a lot of edges, right? Okay, so after we have seen the prompt, let's see how we compute the reward. We have the LM output we call big O, and we let the content between the answer tags, as I mentioned before, as the answers, and we try to parse it into a set of answers because we have undefined number of answers here, right? Since we have undefined number of answers here, we might have a problem of false negative and false positive. That's why we use the F1 score as the reward function. And the intuition is that we want to predict as many ground truths as possible, which is higher recall. And we also want to predict without introducing spurious nodes, which is related to the precision. And the rewards really depends on the model outputs. It encourages the model to discover transferable reasoning patterns across the graphs without constraining their reasoning traces. Here is the objective of the GRPO. I'm not going into details here because it is very, very complicated. Yeah, let's skip this part. If you guys have problem or questions, we will revisit this part. And how did we train the model? If you pay attention to my previous contents, you will notice that actually G1 was training on a 100K training data, right? But in our work, we only collect 1,000 link forecasting queries. I tried to collect these ones in a very equal distributions from all kinds of temporal graphs. So these temporal graphs, TGBL, Wiki, subreddit, CoinFly, they are all from the TGB repository. And I try to collect the graphs with different sizes because they have different metadata, number of nodes, number of edges, node degrees, surprise. I try to cover a diverse set of characteristics when I'm trying to get this because I want to get the representative data for training our model. So this is my final ones, but it is only 1,000. There is some debate between how many, let's say, about how many training data we need to collect for reinforcement learning. From my own experience, I think that 1,000 data is enough because I have observed my own training data, my training curves, everything works well. But for some people, they might think that, okay, the more training data is better. But it doesn't have to be because let's say in the reinforcement learning, we're trying to let the model to learn something by trial and error. If we are only trying to train on this link prediction problem, maybe we don't have to let it discover a lot of diverse patterns. Maybe several patterns are enough. But if we have to let it be excel in all kinds of different tasks, maybe we need to have different data with greater numbers. So it really depends on how diverse your skills, the skills that you want your language model to learn. In our case, 1,000 is enough, okay? So we skip the queries here where the TCGS does not contain all ground truth answers because it does not make any sense by evaluating them. It will always fail language model, right? And also we will also delete the ones where the temporal context graph exceed 600 links because if you pay attention, if you can take a look at the reasoning traces, the output traces of our model, you will see that it was the context window is exploded by these links and it looks very messy. So we try to avoid this part because if it's too long, the language model might not even be thinking. It might be overwhelmed by a lot of links that might not be that related to the prediction. And in the end, we fine-tune a model with our framework called RealTG and based on the Korean 3-4 billion, and we name it RealTG 4 billion. After that, let's see how can we evaluate the forecasting accuracy. I just put MRR here because, well, I think most of the people know, but just in case, I put everything here. And how to compute the rank for node in our QA style formulation. Because now we have the language model returning several answers at the same time. We will assign a node 0 to all the nodes first, and then we try to overwrite it by assigning score 1 to the nodes included in the prediction answers of language model. And we will try to take the mean of the optimistic and pessimistic just following the previous works to get the ranks. And there might be one problem. I'm sorry for putting a lot of text here. The problem is that, let's say, when language model is outputting something, it might always give you false, let's say, yes, false positive, right? It says, okay.
Oh, can you hear me?
Hello.
So we're running a bit over time now, so please wrap up as soon as possible.
Okay.
Reminder.
Okay. So yeah, they might be generating some false positive, and this false positive might make the MRR be very high, but at the same time, actually, it is wrong because it is not in the answer set. So we try to propose something called PMRR, and we try to assign 1.1 rather than 1, ensuring the incorrectly predicted nodes are ranked above correctly predicted ones. And the difference between the MRR and PMRR just tries to help us to quantify the overgeneration problem. And how we evaluate reasoning is that we just use LM as judge. We try to split it into 3 parts: the faithfulness, logical consistency, and answer explanation alignment. And we just use GPT 4.1 to do that. And okay, let's skip this part. If you guys want to know about details, just look at our paper. Let's just skip to the experiment. Okay, the experiment is that we have some seen graphs, we have some unseen graphs. Why we do the unseen graphs evaluation? Just want to show that when we learn from one distribution, can we use this model on other distributions. This is just what GFM are doing, right? We have observed that, okay, the red numbers here are just the best numbers. Our model can outperform even GPT-5 Mini with around 45 in relative improvement. We can also outperform Llama 3.3 70 billion with a great margin. And also for the also when we use the LLM as a judge to do to evaluate the reasoning quality, we also see that our model by training with our framework, it greatly increased the reasoning quality of the language model, and it can be on par with Llama 3.3 70 billion in a lot of cases. And also, we try to see if we try to use a smaller base model, what will happen? We observe the reward hacking, which means that it will try to guess the answer, which helps you to maximize your reward. However, the reasoning is completely a failure. In the forecasting task, it says, okay, this stuff has already been, the to be predicted link has already been seen in the provided graph context, which is impossible. So this happens a lot in the 0.6 billion. And we found that actually, if you increase the model size, you can solve this problem. And for the human annotation, I'm going to skip here because we're just trying to see that whether our LM as a judge and whether our reasoning quality is making sense or not. Right. And the last one is that we tried to compare with G1, and we found that even if G1, they have a 7 billion version, we only have a 4 billion version. Their 7 billion version is also outperformed by our 4 billion version. It means that even the large-scale static graph RL does not transfer to the temporal graphs, which shows the specific challenge of temporal graph reasoning. And the RL over temporal graphs also improves the quality of reasoning traces compared with only doing it on the static graphs. So as a graph foundation model, the model should know how to deal with the static and the temporal graphs together. That's why we think that actually there might be some orthogonal directions going on, but in the end, we can try to combine them together. Yeah. Okay, the last one, summary is that the model post-training techniques have enabled LMs to evolve into foundation models, and the significant challenges remain and require substantial effort to address. Here are 4 questions I'm summarizing here. I'm not reading it, I will stop at this page. And also there are some unavoidable drawbacks. The first is that LM has very large latency, it is very slow. Also, these models are not theoretically guaranteed to capture the diverse graph characteristics. Okay.
Okay, thank you so much, Livon, for the very detailed introduction about your work and some relevant literature as well. So let's give our organizers a warm applause. We really appreciate the time and care you have put into making this tutorial accessible and informative. And actually, do you have the QR code there? Next slide.
No, not which QR code?